A confirmation about the audio, please, guys. If the audio is clear and available, kindly confirm the same. Thank you. We shall be starting in a couple of moments, guys. Ziba, not all of them, but majority of them were moving in the same direction. How to revise the whole current affairs for 2024? Month-wise. Pick it up one by one, month by month, and start covering it from the portion of the magazines that you have. Revise it. So, hello, a very warm good morning to all of you, and welcome to Baiju's Exam Prep IAS. Welcome to another session of geography, where today we shall be furthering our discussion where we left off yesterday. So, yesterday, what is it that we took a look at? Basically, yesterday, when we initiated the discussion for geomorphology, first of all, try to understand the basic formation of planet Earth. There, we observed that planet Earth in itself was not formed in one go. It in itself was created as a result of numerous and significant number of collisions which happened, and collisions amongst dust particles which led to the formation of planetesimals, and planetesimals then they collided to lead to the formation of planet Earth. We also saw that how planet Earth basically evolved to its current shape and form from its earlier state of molten liquid ball of mass. And we observed that how basically it was during the time of formation itself that the stratification of planet Earth's interior happened, where objects and various different materials dependent upon their weight, they started arranging themselves in various different layers. Now, after that, we took a look into the aspect of the sources of information which tell us about the interior of Earth. There we looked at the direct sources and the indirect sources. And based upon those particular direct and indirect sources, we get an idea that overall, the planet is divided in the interior into three basic layers. You have the crust, the surface that we live on. Beneath that, you have the solid mantle. And beneath that, you have the liquid core. Having said that, you have certain anomalies. For example, in the region of the core, the inner part of core is solid and continues to remain in solid state despite the very high temperature because of significant amount of pressure being applied to the innermost portion of the core from all different directions, where the inner portion doesn't have any scope to expand. That is why it continues to remain in a solid state. And there is another anomaly in the region of the mantle as well. Now, as you go beyond a particular depth, due to higher temperature and significant amount of pressure exerted as well, certain radioactive materials which are present in the various different mineral compositions such as uranium and isotopes of potassium, now they start dominating at a depth of around 200 kilometers from the surface. Now, at that particular depth of 200 kilometers from the surface, because of substantial amount of heat, these particular radioactive materials, they undergo a radio thermonuclear reaction. Thermonuclear reaction, any nuclear reaction over a course of its time, it produces heat. And that heat is associated with the term thermo and nuclear reaction, which unfolds. So that thermonuclear reaction basically unfolds at a depth of around 200 kilometers from the surface. Now, at that particular depth, because so much amount of heat is produced in a regional manner, so that means the materials in the surrounding, they partially melt themselves. And they are not a completely molten material, they are not a completely solidified material, they are partially molten, partially solid. So that is a region which is considerably a weaker portion in the part of the mantle itself, and that is what we regard as the asthenosphere. So that is what we had studied up till yesterday. And we further continue our discussion. And today we shall be covering the portion of rocks and also the theories such as the theory of continental drift, the theory of convection current, the seafloor spreading theory, and how all of them eventually led us to the formulation of the plate tectonic theory, which is followed up till this day. Now, starting with the portion of crust. Okay, the crust. Biswajit, I read the Hindu newspaper for the first time but I could not understand anything. Is it the language that you could not understand, or is it the meaning of it that you could not understand? Once you cover the basics of GS, there is no reason why you should not be able to understand that. And any part that you are unable to understand, then that is why we have the analysis, newspaper analysis also. If the language is very tough, switch over to Indian Express. Indian Express will have an easier language, but before that, I would tell you that try to continue with this particular practice for at least 10 days, and then slowly and steadily the understanding will come. Now, when we talk about the crust is the topmost surface of the planet Earth. Crust is the surface that we live upon. It is significantly hard and brittle, but it is not very significantly thick. It is very, very thin. The thickness of the crust ends up varying when we talk about the continental areas, and when we compare it to the oceanic areas, the thickness of the crust keeps on varying. So it is the outermost solid part of the earth, and it is brittle in nature. Brittle in nature means it cannot be stretched and compressed quite significantly over a period of time. Let's suppose if you are stretching it significantly, it will break from between. So that is what is brittle, that it breaks easily. Cracks and ruptures easily. Okay. Now, the thickness of the crust, it is variable under the continental areas and also slightly variable under the oceanic areas. Generally, under the oceanic areas, you will find that the crust is much thinner. Under the continental areas, you will find that the crust is much thicker, significantly thicker. So oceanic crust is thinner as compared to the continental crust. Mean thickness of the oceanic crust is only roughly around 5 kilometers. In certain cases, that crust might be thicker, maybe around 7-10 kilometers at max, but not generally more than that. In very rare cases, will you find the oceanic crust to be thicker than 10-12 kilometers. But generally, the thickness is only around 5 kilometers to 10 kilometers. Whereas when we talk about the continental crust, now the thickness of continental crust is around 30 kilometers. Right? Now, having said that, this is not going to be consistent throughout the entirety of planet Earth. For example, in certain areas, for example, if you consider the regions such as the Himalayas or certain fold mountains, you'll find that those are created, as we will study later on, those get created due to the compression of the crust. That is how the fold mountains, etc., such as the Himalayas, they get formed and they get created. So that is when, whenever you have a crustal compression happening, in those areas, the thickness of the crust significantly increases. So, for example, continental crust is thicker in the areas of major mountain system and can be as much as 70 kilometer thick under the Himalayan region. So it is not always consistent, but in certain areas it will be very high, around 70 kilometers, but in majority of the areas it will be around 30 to 35, 40, 45 kilometers. That is the thickness of the continental crust. Now, there is a difference in density. What is density? Density is mass per unit volume. Density is mass per volume. Okay. So in the region of the continental crust, you'll find that the density is close to around 2.7 gram per centimeter cube. It is chiefly composed of granitic materials. And that is where the density is 2.7 gram per centimeter cube. Whereas in the case of the oceanic crust, they are made out of basaltic rocks having a significant proportion of iron, magnesium, and these kind of minerals. So that is where the density is close to around 3 gram per centimeter cube. So oceanic crust has got a greater density, whereas continental crust has got a lesser density. Now, this is the reason why, regardless of the thickness that is accrued to them, continental crust is always going to be lighter as compared to the oceanic crust. I will repeat, regardless of the thickness under consideration, continental crust will always be lighter. Why? Because of the factor of density. Because continental crust has got lesser density. If you want to think about the analogy of it, think about it. Let's suppose you have a sheet of iron, right? Which is going to be not very thick, a thin sheet of iron. Next to it, you keep a thick sheet of thermocol. Thermocol might be twice or thrice or four times the size of the iron sheet. But if you measure the weight of it, always the iron sheet will be the heavier one. Isn't it? Thermocol will be lighter than the iron. Why? Because of density. Thermocol is very light because of lower density. Iron sheet is going to be very heavy because of the higher density. It is basically this reason why we observe that the oceanic crust is always heavier than the continental crust. Okay? Oceanic crust is always heavier than continental crust. Okay? Regardless of the thickness in consideration, due to higher density of oceanic crust. So because of higher density of the oceanic crust, you will find or you will come across a scenario where the oceanic crust is always going to be heavier. Okay, its role basically is something which will be very apparent to us when we talk about the theory of continental drift, the theory of plate tectonics, etc. And this leads to different types of geomorphic actions taking place as well. So this is something which you observe a kind of a phenomena. Having said that, those of you who will read the NCRTs, this is a fact which is mentioned in NCRT in a wrong manner. Okay, so in NCRT, it states that the continental crust has got a greater density, whereas the oceanic crust has got lesser density. So please be aware of that. NCRT has got its fair share of mistakes as well. So that is why you can verify it from the portions and the regions that you have covered in the class. This is one of those areas where the NCRT sadly has committed mistake there. Okay. Now, then we come to the bulkiest portion in the interior, and that is the mantle. Now, the mantle, it initiates, or the mantle portion in itself, that is present immediately underneath the crust. Now, the crustal thickness in the majority of the cases is maximum around 35 to 40 kilometers. at max 40-45 kilo. It is only in very rare cases such as the Himalayan region where you have crustal compression, where it has gotten thicker and as thick as 70 kilometers underneath the Himalayas. But in general, what is the thickness of the crust? Around 35-40 kilometers under the continents, 5 to 10 to at max 20 kilometers under the oceans, isn't it? So immediately beyond that, you have the onset of the mantle. Now, mantle is solid. It is a different matter altogether that at a particular depth in mantle, at a depth of around 200 kilometer and so on from the surface, you will find the presence of asthenosphere. But before the asthenosphere, you will come across a solid portion of mantle as well. So if you can think about, if let's suppose this is the outer surface, this is the region of the crust, right? Then you will come across the layer of the mantle, and within that layer of the mantle, you will have the presence of asthenosphere. Here, you'll find the presence of asthenosphere. Okay, so the crust, this is your crust, this is the solid upper mantle. So the crust and the solid mantle together, upper solid mantle, together they are referred to as what? Together they are referred to as, very good, lithosphere. Good. Together we know them as lithosphere. So mantle basically, if you will observe, it extends immediately underneath the crust, and it extends up till a depth of around 3000 kilometers from the surface. So the extent of mantle is very huge. Almost up till a thickness of 3000 kilometers is where the mantle exists and extends from. Observe here. This is the portion where the crustal portion ends, and observe how underneath that the mantle extends up to the depth of 2900 kilometers. In that, in the upper portion itself, you have the semi-molten, semi-solid asthenosphere, which is also present and which is also to be found in that area. Now, mantle represents close to around 68% of the Earth's mass. 68%. Now, when we talk about the lower portion of mantle, this is also solid, by the way. This is also solid. But here, when we talk about the lower portion of the mantle being solid, understand that in this condition, the density is very high. Imagine a kind of a solid where the density is so very high, heat is also so significant that you can deform that region, you can compress it, expand it, and basically it won't rub against each other. These solids, they won't be rubbing against each other, but whenever there is a push or pull, they can have a kind of a compression or a deformation action. So that kind of a solid. Remember the analogy of coconut that we provided yesterday, that the earth's interior resembles that of a coconut, where we observe that the outer harder shell of the coconut is representative of the crust, which is very hard, but it is very thin at the same time. And then the pulpy white solid that you have in the case of the coconut. Now, something very similar is present in the mantle. Now, if you recall that pulpy white thing, substance in the coconut, you can compress it, right? You can deform it. It won't break very easily. So a similar property is also observed in the region of mantle. It has a density of close to around 3.4 gram per centimeter cube, which substantially increases by the time that you reach the lower portion of the mantle. Having said that, on an average, it is around 3.4 gram per centimeter cube. As we go into the depth, here you will find that you have the presence of asthenosphere. Now, the word asthenosphere in itself is derived from the term astheno, which means weaker. It is considered to be extending up to a depth of 400 kilometers from the surface. Up to 400 kilometers from the surface. So you can think about it that the thickness of asthenosphere in itself will be close to around 260 or 200 to 250 kilometers. That will be the thickness of asthenosphere, because the lithosphere, the entirety of lithosphere, that is the crust and the upper solid mantle, that thickness will be roughly around 100 kilometers or 150 kilometers. So thickness of lithosphere is around 100 to 150 kilometer. It is beyond this that you will find the presence of asthenosphere. And here we have already seen why there is so much amount of heat, because of thermonuclear reaction which is observed in the radioactive materials which are present in high concentration at this particular depth. Okay, it is the main source of magma or the molten materials which erupt out of the earth's surface whenever you come across any volcanic eruption. And wherever volcanic eruptions happen, the molten materials that come out, they are generally supplied from the region of asthenosphere in itself. Okay, now then we come to the portion of the core. Now core is the innermost portion. It is dominated by minerals such as iron and nickel. And we have seen that when the iron and nickel, that portion, those particular elements, basically they accumulated around the region of the core right since the time of formation of the planet. At the time of formation of the planet, iron and nickel were the most bulky objects out there. And that is what started dominating the core region. So it is still dominated by iron and nickel only, right? If you think about it, that you have many elements which are heavier than iron and nickel, so why is it that those elements are not present in the crust, or those elements are not present in the region of the core? Why do you think that is the case? When you have elements such as uranium, plutonium, potassium, all these heavier elements are present, but still you'll find them closer to the surface and not present in the region of the core. That is because the layering had been done when everything was molten. At that point of time in itself, the layering had been achieved. Once you have the solid structures getting created, regardless of how hard or how heavy those solid materials are, they will never be able to sink exactly to the bottom. That is why even today, iron and nickel, they are the dominant one. And that is why the region of the core is also referred to as the Nephe layer. Nephe in the sense, Ni stands for nickel, Fe stands for iron. So that is why the core is also referred to as the Nephe layer. Now, having said that, when we talk about the region of the core, we know that the inner core is in solid state, whereas the outer core is in a molten state. And the inner core being in solid state, basically, why is it so? Due to very high amount of pressure. Okay, right? I hope that is understood. Now the width of the core from, so the total radius of planet Earth is 6370 kilometer, right? Now that is the radius of it. The core starts at around the depth of 2900 kilometer. So you can think about it that the thickness of the core will be roughly around 3400 kilometers, right? That will be the thickness. The density also becomes higher. It comes close to around 7 grams per centimeter cube. That becomes the density. So the density also keeps on increasing. Okay. Now we come to the portion of discontinuities. Does magma erupted from volcanoes contain radioactive materials? No, it does not. See, certain any mineral that you find, any type of major rock that you find out there in the nature, right? And listen to this carefully, because many of the times, and that is a normal misconceived notion that many of us have, when we think about elements such as uranium, when we think about elements such as plutonium, we think that they would be present in large chunks somewhere. Even if they are present in lesser amount, they will be radioactive, and that will be explosive in nature. But that is not the case. Even, for example, when you have granitic rocks, those granitic rocks will also have traces of uranium. Very little traces of uranium, but it will have those traces of uranium. When you talk about basaltic rocks, they will also have some radioactive elements in very small traces, right? So in very small amount, that will be found. But then when they are heated beyond a particular range, then while all the other materials, they will melt, these radioactive elements, when they are present in larger concentration, they will not only melt, they will undergo a nuclear reaction also. But for that, you need that high temperature in the tune of hundreds and maybe 1,000 degrees Celsius and more. So in that case, that is why all this happens in the region of asthenosphere. Now, Anu, you had a question, and your question was that upper portion of the mantle is asthenosphere. Then how upper portion of mantle is asthenosphere? Then how upper mantle is asthenosphere? Wow. Upper portion of mantle below is asthenosphere. Then how upper mantle is asthenosphere? I understand the predicament. The question maybe that you are trying to ask, that upper portion of mantle is included in lithosphere, then how come we are saying that upper portion of mantle is asthenosphere? It is a matter of semantics. It is a matter of understanding. Listen to this carefully. This is your mantle having a thickness of 3,000 kilometers. Okay, here you have the presence of asthenosphere. Let me represent it by different color. Here you have the presence of asthenosphere for around, let's say, 150 or 200 kilometers. You have the presence of asthenosphere, right? Now, this portion of solid mantle which is present above the asthenosphere, what will we call them? Will we call them upper mantle? Will we call them lower mantle? Or will we call them the innermost mantle? What do you think? This solid portion of mantle which is left beyond the asthenosphere, can't we consider that as a portion of upper mantle itself? When we talk about asthenosphere, what will we say? Will we say that it is present in the middle of the mantle? Is it present in the lower portion of the mantle? Or can we say it is present in the uppermost portion of mantle itself? What do you think? So that will also be present in the uppermost portion of mantle, because the thickness of mantle is 3,000 kilometer. And the end of mantle that we are talking about, this entire end that we are talking about, is only about 400 kilometer. I hope that is understood. Isn't it? Good? Right. Core thickness is more than mantle, but you're saying that mantle covers more percentage because the outer core is in liquid state. So it is there that the density reduces. Okay? The source of magma is asthenosphere, yes. Kambapati, I hope that gives your answer as well, and Pratik, your answer as well. And Shyam, I hope you also understand. See, when we say the core also consists of molten materials, right? The outer core. What is the thickness of outer core? Take a look at this image again. So when you observe the region of the outer core here, this also extends, the liquid portion extends for almost 2,200 kilometer. Okay, that is the thickness of it. 2,200 kilometer is the liquid molten portion. So that will be comparatively lighter. When we talk about the lower portion of mantle, that is very, very dense. In the lower portion of mantle, you will reach a density of close to around 7 to 8 gram per centimeter cube. Right? That is why when considered in the entirety of the region of the mantle, the entirety of the portion of mantle is bulky enough. Okay? Right? Now, source of groundwater. Source of groundwater, okay, if we are using this scale, so let me tell you how insignificant the groundwater is in terms of its presence. So let's suppose you have this as the crustal layer. This as the crustal layer. Now within this crustal layer, that too in the uppermost portion of the crust itself, you will have within the rocks presence of groundwater here and there. So all the groundwater that you are extracting, what is the depth from which you extract the groundwater? How many of us had the kind of a notion that we are extracting groundwater from the region of the core? I hope that was not the preconceived notion anybody was carrying. Groundwater is present. 100-meter is also very, very deep, right? So in regions where you find groundwater at a depth of 100-meter means groundwater has been depleted in that region mostly. Maximum you will find around 60 feet, 80 feet, right? Rare instances, 100 feet, but mostly it will be present within 10 meters, 20 meters, 60 meters at max, right? So that is the presence of groundwater. We are not even talking about kilometer here. Thickness of crust is how much? Thickness of crust in continent, obviously you are extracting groundwater from the continental areas. I hope none of us have experienced the extraction of groundwater from the oceanic areas. We are extracting groundwater from the continental areas. So there the thickness of crust is 35 kilometers, but we are extracting groundwater from where? At a depth of few meters, right? So you can think about that, how closer to the surface will you find the presence of groundwater. Okay. And Balaraju, so then in our area, groundwater is available at 330 meters. So you might be talking about the region of Peninsular Plateau in the southern part of India. That is where, because of the plateau structure, the groundwater is present at that particular depth. Pratik, one basic question in how lower density outer core settle down beneath the higher density mantle. It is not that the lower density core, see, outer core, it won't be the case that it has very little density. Outer core's density will still be comparable to the density that you find in the middle portion of mantle. It is just that due to very high temperature, the portion has melted out, right? If the temperature would not have been so very high enough, it would not have melted out. So that is why overall, if you consider the entire region of core, on an average, the density will be higher as compared to that portion of the mantle. Okay. So the density of the core is roughly around 7 gram per centimeter cube. That will be the density, significantly larger in the portion of the inner core. The density can go as high up as even 12 to 13 gram per centimeter cube. But on an average, it is around 6 to 7 gram per centimeter cube. On an average, mantle's density is 3.4 gram per centimeter cube. Now, when we talk about the various different layers, these layers, they subtend a pressure on top of each other. They exert a pressure, they exert a weight on top of each other. For example, if you think about it, let's suppose you have a particular stone that you keep on the table. Nothing will happen. You push a larger rock on the table, maybe your table will break, the table will collapse. You push a even larger rock on the table with greater weight, it will get compressed. If you further add on to the weight, it will completely get deformed. So just like that, as you go into the depth with many kilometers, the pressure exerted from top keeps on increasing. And due to that increasing pressure, the material density starts to change, the particle arrangement starts to change, the mineral distribution starts to change, and everything shows a kind of a change. So as you go into the depth in each of these layers, be it in the region of the crust, be it in the region of the mantle or the region of the core, beyond a certain depth, you have a different set of materials in terms of particle density, etc., exerted due to the overlying pressure. So you have certain zones of transition which demarcate those different properties. For example, in the region of the crust, between the upper crust and the lower crust, you have a discontinuity, that is the Conrad discontinuity. And that Conrad discontinuity basically indicates the difference in the types of materials that you have beyond a certain depth in the crust, right? When we talk about the continental crust is dominated by elements such as silica and aluminium. That is what you find to be dominant in the region of continental crust. That is why continental crust is also referred to as Sial. Whereas when we talk about the oceanic crust, which is present at a greater depth, that is enriched with silica. Silica is SiO2, okay, silicon oxide, dioxide. So silica and magnesium, and this is referred to as SEMA. So even in the region of the crust, you will find that at a particular depth you will have different set of materials. At an upper portion closer to the surface you will have different set of materials. So that is demarcated, that difference is demarcated by a discontinuity, the zone of transition, and such discontinuities you will find to be present across the entirety of the interior of the planet. So for example, you have the Conrad discontinuity between the region of the upper and the lower crust. Then the crust and the mantle in itself, they will have a different property. So that is separated by another discontinuity, which is referred to as the moho discontinuity, or the moho in itself, sometimes also referred to as Mohorovičić, the name from which it has been derived from, right? The individual from whose name it has been derived from. So that is how you have the Mohorovičić discontinuity, okay, or simply referred to as moho. So in geographical analysis and research papers, you will find, for example, whenever an earthquake occurs, in certain analysis of those earthquakes, you will find that it is said that, okay, the earthquake has occurred 5 kilometers above the Moho, right? The earthquake has occurred 10 kilometers below the Moho. Earthquake has occurred at the region of the Moho. So that tells you that the reference point is the Moho discontinuity or Mohorovičić discontinuity. Then the upper portion of the mantle and the lower portion of mantle, they will also have differential properties, where the lower portion of mantle, due to higher amount of compression, higher amount of pressure, there will be deformities, etc. So that is what is indicated by Repiti discontinuity. Okay. And then the outer core, which is liquid, and the mantle, which is solid, they are separated by what is referred to as the Gutenberg discontinuity. Okay. And then you have the outer and the inner core. Inner core is solid, outer core is liquid. So that is named by the individual who first of all came upon the finding and the discovery that inner core indeed is in a solid state, and that is how it is named as Lehman discontinuity. So these are your discontinuities relevant for your prelims examination. This will be relevant for your prelims examination. Now, for your general studies, out of all of these, let me tell you, for your general studies, not all of them are important. For your general studies, ideally, Mohorovičić, that is between the crust and the mantle, and also Gutenberg, that is between mantle and the core. These discontinuities are going to be relevant for your GS, but other areas, it will always be rewarding if you are aware of the other regions as well. Okay. Now, here, when we talk about these particular kind of discontinuities, they are present in each of the layers. Now, when we talk about the various different types of minerals in the interior, this is again one of the favorite areas for UPSC prelims. So here, generally you get questions which are asked that which are the minerals which are most dominant across the entirety of the planet, which is the mineral most dominant across the surface. So such kind of questions have been asked previously. It is not being asked in the past couple of years, but it has been asked considerable number of times, so you should be aware of that. So when you consider the mineral distribution, earth as a whole, the entirety of the planet, if you consider, so it is most dominant with iron, followed by oxygen, then silicon, magnesium, sulfur, so on. Now, ideally, do you need to learn all of this? No. Ideally, just the top 4 will be sufficient. Okay. Now here you observe oxygen is also very dominant. But oxygen is a gas, isn't it? So which oxygen are we talking about here? Here we are talking about oxides. Oxygen reacts with any material to form oxides, right? Iron oxide, aluminum oxide, silicon oxide, etc. So that oxide form of oxygen. So you can think about how much different types of, or how many different types of oxides are present. So iron is the most dominant element across the entirety of the interior. Having said that, when you consider only the Earth's crust and only the Earth's surface, it is mostly dominated by oxygen, followed by silicon, then aluminium, then comes iron. Why? Because remember we told you that and we talked about the fact that continental crust is composed of silica and aluminium, right? Now silica and alumina rather. Now both of them consist presence of oxygen. Silica also has oxygen, right? And even when we talk about the oceanic crust, that is SEMA, here also you have silica, so that will also have oxygen. So that is why oxygen is the most dominant element on the Earth's crust, on the Earth's surface. We are not talking about atmosphere here, we are talking about the Earth's surface. So oxygen will be the most dominant element which is to be found. Okay, right? Now, here, when we talk about it, basically, this is the kind of a question which can be framed from here. So take a look at this particular question where it is a kind of a match the following kind of a question. Conrad discontinuity between the upper and the lower crust, Morovicic discontinuity between the outer and the inner core, Repeti discontinuity between the upper mantle and the lower mantle, Gutenberg discontinuity between the Earth's crust and the mantle. So which of them are correctly matched? Let me know. Good. Majority of you have given the correct answer. So here, basically the Conrad discontinuity between the upper and the lower crust, that is correctly matched. Morovicic discontinuity is between the crust and the mantle. So this is incorrect. This is between crust and mantle, right? Repeti between the upper mantle and the lower mantle. So this is correctly matched. Gutenberg between the mantle and the core. So that is incorrectly matched. So here the correct answer is going to be A, 1 and 3 only. Okay. Now, after this, and before moving into the portion of rocks, let us talk about another concept here. And let us talk about the concept of geomagnetism. Geomagnetism. What is geomagnetism? Geomagnetism, basically, geo here refers to Earth, and basically this term represents the magnetic properties represented by planet Earth. Now, planet Earth behaves like a magnet, and that is purely because of the presence of liquid or molten outer core. Now, outer core consists of, or inner core and outer core, both of them are very dominant in iron and nickel. Iron and nickel both are having magnetic properties, right? But the presence of, so if iron and nickel would not have been present in such great proportion in the region of core, maybe magnetic property would not have been experienced. But then, if let's suppose the outer core and the inner core simply had the presence of iron and nickel, that in itself is not sufficient to generate magnetic properties. But the entire rotation of planet on its axis. So when the planet rotates on its axis, Here, let's suppose we consider the planet. Now, when the planet rotates on its axis, even the region of the outer core will also be rotating on its axis, right? You have the region of the solid inner core also. But overall, if you consider molten outer core, molten outer core. Now, this is rich in iron and nickel. Nife, isn't it? So, as the planet rotates on its axis, can we imagine a situation or a circumstance where this liquid outer core will also rotate? But when we talk about this liquid outer core, what does your imagination tell you? Is it going to be like water, that fluid like water? No. Here you will find a kind of a viscous liquid which doesn't flow very easily, right? I hope you would have seen, for example, honey. Honey is also a liquid, isn't it? When you consider, let's suppose, tar is also liquid. But does it flow at the same rate as you consider the flow of water? Obviously not. Honey will have a much difficult time in flowing around, whereas water can flow easily. So density will be different, right? So because the density is very high at the region of the core, that rotation which will happen, the rotation will go on. Rotation of outer core will happen. But it is not going to be very smooth rotation as you observe on the surface. It is going to have its own inertia, has its own particular momentum associated. Now, when the outer core rotates, here the property of outer core needs to be understood. Temperature, very, very high. Elements, iron and nickel, which are magnetic in nature. So, at very high temperature, when iron and nickel are going to be present and they are going to be moving around, chances are that the atoms which are present, the atoms of, let's suppose, iron, which is present, chances are that the electrons of those atoms will escape, isn't it? So you will have iron and nickel ions which get created, which get formed in certain portions of the interior of the portion of the core. Now, as they rotate, they will generate a kind of a magnetic field which is perpendicular to it. So as they keep on rotating, basically, as you would have observed, I don't know how many of you have studied science. Let's assume nobody has studied science in your graduation days or your pre-graduation days. But you would have, if you don't know, then you should know about it, that when current flows in a kind of a spiral or a circular fashion, whenever the current flows in a spiral or a circular fashion, it generates a magnetic field perpendicular to it. Right? So here also, you will have the presence of ions. Ions means charged particles, charged atoms which are present. So those charged particles of iron and nickel, as they move around in a circular manner, they will represent or they will mimic a similar property. So as a consequence of that, they will be able to generate a magnetic field which will be perpendicular. They will be able to generate a magnetic field which will be perpendicular. Okay. So that is a property that you will observe. Now, had the core not been rotating, or let's suppose had the core been completely solid, then this magnetic field would not have been generated. It is the fact that the outer core is in molten state. So, and as they rotate, basically, you will find that there will be significant amount of these ions moving in a circular manner. So they will generate a magnetic field which is perpendicular. And that is when the planet Earth starts behaving like a bar magnet. And that is what is referred to as GEO, magnetism or the magnetism of planet Earth. Okay, I hope we are comfortable up till this point, right? Good. So now when we are comfortable up till this point, let us understand the further greater concept associated with that. Now we talk about the region of outer core being viscous in nature, not very fluidic in nature. So generally, you will find that you have certain large bulk of iron, nickel, etc. that starts concentrating. For example, you will have as the because not when anything doesn't flow easily, always find an analogy with that of flow of honey. Honey also, let's suppose when you are pouring it in a jar, immediately it will not have a uniform thickness, uniform density. Certain areas will have a larger bulk concentrated in one portion. Certain areas will have maybe lesser bulk, lesser density created because air has penetrated, etc. So here also, when the outer core is rotating, sometimes what might happen, you might have accumulation of large bulk of iron and nickel in one region. Molten itself, but might have a larger concentration. Now, if you have that larger concentration present, let's suppose somewhere here, chances are that the magnetic field will change. The magnetic field will start coming from here. Because that magnetic field is generated by what? It is generated by the presence of that iron and nickel. Right. So wherever they will be found in much greater density, there will be a variation indicated. So that is why when we talk about the magnetic field of the planet Earth, it has changed hundreds and thousands of times ever since the formation of the planet. Right. So that magnetic field keeps on changing. Having said that, now we are able to calculate with the help of computer simulations. We are able to calculate that maybe 5 million years ago, what would have been the magnetic field of planet Earth? 400 million years ago, what would have been the magnetic field of planet Earth? So we are able to calculate that with the help of the various different supporting rock structures, etc. We are able to basically calculate the geomagnetism of the past as well. Right. So that comes under the category of the study of the age of the rocks based upon their magnetic properties. That is something which we refer to as paleomagnetism. Paleo means study of something which is very, very old. Having said that, geomagnetism, again coming back to it, geomagnetism is the magnetic field extended by the earth because of dominance of iron and nickel in the molten form in the outer region of core. That is your geomagnetism. Okay. Now, this geomagnetism or the magnetic north and south pole, they keep on changing their position because the presence of iron and nickel, that is not going to be uniform throughout. Sometimes in certain areas you have a bulk of concentration of iron and nickel, and over a period of time it might shift ever so slightly. For example, for the past few decades, for the past decade and a half, 10 to 15 years almost, prior to 2020, what was being observed was the fact that in the region of the core, you have, or the when we talk about the region of the magnetic poles, it was being observed that the magnetic pole is ever so slightly shifting. Magnetic north pole in particular has been ever so slightly shifting. Now, this intrigued the scientists. And what is the relevance of the magnetic poles and the magnetic field, by the way? All the compass that you have, the GPS readings, the compass readings, etc., that you have, all the compass points north, isn't it? So all of that is aligned with the magnetic field, right? It is because of the magnetic field that they are able to point north. Now, it was being experienced that the magnetic north pole across the planet, that is shifting slightly underneath the region of Siberia. Upon greater study, it was found out that you have a large bulb or large mass of iron and nickel in the region of outer core, which is shifting slightly under the region of northern and northeastern Asia. Finally, it shifted and settled down underneath the position of Siberia. So that is why Recently in 2020, you had the magnetic north pole of the planet, which shifted from the region to the north of North America to the region of underneath Siberia. So that is why these poles, they are prone to shift. They are prone to change owing to the changing concentration that you will find in the region of outer core. Okay, the concentration of iron and nickel as they change from one region to another, you will find that there will be a dominance or a change in the corresponding magnetic field also. Okay, now these magnetic field basically, that is also relevant whenever we talk about earth and sun interactions. For example, when you consider the sun consistently over a period of time, very periodically over a period of time, it continues to release charged particles in the form of coronal mass ejections, solar flares, etc. The sun and the solar winds, etc. The sun continues to release significant amount of charged particles. Okay. Now these charged particles, photons, etc., these charged particles, they travel with very high speed of hundreds of kilometers, thousands of kilometers per hour per second. They move through the entirety of the solar system. Now, these charged particles, they interact with the magnetic field, and they interact with those areas where the density of magnetic field is the highest. So when you talk about planet Earth, right, here let's suppose you talk about planet Earth. Let's suppose. And here, let's suppose you talk about the presence of the magnetic field of planet Earth. Okay. Now, where you will find a greatest density of these magnetic field is going to be closer to the region of the poles. Around the region of the poles, you will find very high density of these magnetic field lines, isn't it? Now, let's suppose that when the solar activity takes place, if this is the sun releases charged particles. Charged particles. Now, these charged particles, they get shaped, and their interaction gets shaped by these magnetic field lines. They will be attracted and diverted towards those areas where the magnetic field line is very high in density. So let's represent charged particles with a different coloration, blue coloration. So these charged particles, they get diverted here, and they will have an interaction in these areas. Interaction with what? Interaction with atmosphere. Oxygen and nitrogen present at a height of 100 kilometer, 200 kilometer from the surface. Those gases, they interact with these charged particles. Okay. And in these areas, as these charged particles will interact with oxygen or nitrogen as a molecule, think about it. When you have, let's suppose, an atom of oxygen or nitrogen, a charged particle hits it. Chances are the energy that will be provided by the charged particle, with that energy, maybe an electron will escape from the system, right? After some time, it will lose its energy, it will come back to its normal position. So, whenever that electron comes back to its normal position with the oxygen or the nitrogen atoms, they produce light. A unique hue of light is produced: blue, green, purple to pink to slightly yellowish. Those kinds of light are produced. So the night sky gets dominated by those particular lights. These lights are observed in the higher latitudes, that is closer to the region of the poles. The region closer to the equator are referred to as lower latitudes because the naming is 0 degree, 1 degree, 10 degree, etc. So hence lower latitudes refer to the region around equator. Higher latitudes, they represent the regions around the poles. So in the region of the higher latitudes, where you have a greater concentration of magnetic field lines, these charged particles, they interact with these gases around this region, and they produce beautiful light in the night sky. And they are referred to as by the name auroras, not aurora. Aurora is a title that you have in the region of Punjab. This is aurora. Okay. In the northern hemisphere, they are referred to as aurora borealis or northern lights. In the southern hemisphere, they are known as aurora australis or southern lights. So, that is something that you observe in higher latitude. That is why every year you will find tens and tens of thousands of people visiting the region of Norway, visiting the region of New Zealand, visiting the region in Greenland, and in the region around Argentina. Why? To witness these lights. Right? They basically cover the entirety of the night sky, and they give that very beautiful greenish to green, blue to pinkish appearance many of the times. Okay. Now, by the way, you would have heard about the Aditya L1 mission. All of you would have heard about the Aditya L1 mission that India has launched. Amongst the various works which will be carried out and the various experiments which will be carried out by the Aditya L1 mission, one of the important work or the experiment that it will carry out when it is parked in its final position is going to be that how these charged particles they get deviated to the region. What is the change in the angular momentum as these charged particles they get deviated to the region of greater magnetic field line concentration. So that is something which you will which Aditya L1 mission will carry out the experiment for, and Aditya L1 mission will help us know more about these northern and southern lights, why they are formed, where they are formed in the coming days also. Okay. Argentina is not in polar region, but is Norway in polar region or is New Zealand in polar region? No. In higher latitudes, you witness that. Okay. Right? Study of sun done by Aditya L1 has got many different types of mission. One of them is the study of the sun. Right. Yes, Atharv. That is correct. So that is the case of geomagnetism and the impact of geomagnetism. Okay, so geomagnetism overall, again, if I have to summarize, geomagnetism is subtended because of the molten outer core consisting of iron and nickel. Now, iron and nickel themselves are magnetic in nature, but in their own, they cannot generate a magnetic field, or a magnetic field line cannot be generated if you keep iron somewhere. So basically, you have the molten iron and nickel at high temperature as they are basically rotating. So that generates a perpendicular magnetic field that is referred to as the geomagnetism. Now, here, this magnetic field of the planet Earth that continues to change ever since you will have, or whenever you will have a change in the density of the region of the outer core. So there also, this will continue to change. This change will be experienced as well. This change will be observed by the shift of the magnetic poles. So throughout the history of the planet, the magnetic poles have been shifting quite significantly. The most recent one was when the magnetic North Pole shifted from the region of North America to the region underneath Asia, in underneath the region or around Siberia. So that is where the magnetic poles keep on changing. Okay. Now, here, when you have these magnetic field lines, basically they have in those areas where the magnetic field lines are of greatest density, in those areas, the charged particles interact with the oxygen and nitrogen atoms, and their interaction produces a hue of light. So that is where, when these charged particles they interact with them, that produces the presence of these kind of lights, in which are referred to as northern lights in the northern hemisphere, southern lights in the southern hemisphere, or aurora borealis in the northern hemisphere, aurora australis in the region of southern hemisphere. Now we come to the portion of rocks. So once we talk about the region of the rocks, now here we shall be covering the basics of the rocks, that is igneous, sedimentary, metamorphic, etc. Now this basics can be relevant for your prelims as well as for the mains. So for your prelims here, basics of rocks, okay, their types, and in the mains, again the same portion, basic properties of rock systems, even rock cycles. Okay, so here, when we initiate the discussion about rocks, so what are rocks? Rocks are basically mineral aggregates with a combination of properties of all the different materials which are present in it. Something that you encounter on your day-to-day basis. When you step outside your house, you will observe some or the other type of rock which you will come across kept here or there. So rocks you will encounter on a day-to-day basis, right? Now rocks mostly will consist lot of different types of materials included within it. Included within that solid structure, you will find lot of various different materials. So that is why the general property of the rocks is a combination of the properties of the individual materials considered. So any unique combination of chemical composition, grain size, texture, or other distinguishing characteristics is used to describe the various rock types. Broader classification of the rocks can be done as igneous, sedimentary, and metamorphic rocks based upon their formation, right? Based upon the process of formation. So this classification is done based upon the process of formation. So based upon the process of formation, you have the igneous, sedimentary, and metamorphic. What do we mean by igneous rock? Igneous refers to something which is incendiary, which is a result or resultant of fire. So these are the rocks which get created by the cooling down of molten materials, right? Cooling down of molten materials, and when they solidify, they form igneous rocks. Now that cooling down can happen on the surface. Sometimes that cooling down can happen in the interior itself. So depending upon where that cooling down has happened, you have the classification of igneous rocks. But when we talk about igneous rocks, they form as a result of solidification of molten materials. Now these rocks, easily you can imagine, these would have been the first kind of rocks to be created, isn't it? Whenever the planet would have started cooling down, whenever the planet would have started solidifying, these would have been the rocks which would have been created, because cooling down of molten materials. So that is why these are also referred to as the primary system of rocks, right? These are also the first kind of rocks created across any landmass. any landmass that you come across, the first rocks ever created, when a new land gets created, when a new land is formed, the first rock to be created is the igneous rock formation. Okay, so these are also referred to as the primitive rock systems or the primary rock systems. Primary rock systems. Now, if you think about it, apply your logic here. When we talk about the rocks, igneous rocks, they have been formed by what? Solidification of these molten materials. So, will these rocks have within them the presence of animal or plant fossils or remains? Do you think they will have the presence of organic matter within them? Perfect. Absolutely no. So, they will not have any kind of organic compound within them. That is why when we talk about, when we will later, at a later point of time, we will be talking about the formation of soil, that how soil that we see around, how that gets created. We do know that soil basically is created after the breaking down of the rocks. When the rocks break down quite substantially, soil gets created. That is why the soil which is created out of igneous rocks, you will never find organic component or organic materials present within them itself. Okay, because the parent rock in itself, that doesn't have any amount of organic compound, any amount of animal or plant remains. Then you have sedimentary rocks. Sedimentary rocks, as the name suggests, has been created as a result of the process of sedimentation. Now, this process of sedimentation, what is this process of sedimentation that we are talking about? So let's suppose a river is flowing somewhere. Let me use this particular slide. Let's suppose igneous rock, why black in color, always how? Who told you igneous rock black in color, always how? Igneous rock can be different in color always also. Look at this. Is this black in color? No, this is an igneous rock. So who told you igneous rock is black in color? Sometimes the set of information that you guys provide, it makes me so very much interested to inquire more that where you have come across these. Okay, so I hope that is clear now. Igneous rock will not always be black in color. Coloration factor of the rocks is dependent and driven by the minerals which are present. You will have even the igneous rocks getting classified into felsic and mafic and ultramafic. So the blackish color that you are talking about, that is of mafic kind of rocks, which is dominant in magnesium and iron. Okay, whereas ultramafic that is present, that will be greenish in color, greenish in appearance. Felsic that you consider, that will be whitish in appearance, brighter in appearance. Okay, lesser in density also. I I don't want to jump multiple loops to go into a concept which will confuse you. That is why I'm telling you. Yesterday also I told many of you, have patience and have a little bit of trust. Just this much is what I ask. Trust me, by the time that we reach the 24th or the 23rd module, you won't find a topic that I have heard about this, but that has not been covered, unless and until you are talking about facts such as Bermuda Triangle, what happens in Kailash range, or whether Ram Setu is real or not. Those kind of issues or problems I won't be able to solve. But other than that, trust me, any issues that you have, anything that you would have heard about geography, we will cover it much deeper and in a much more authentic manner that what your WhatsApp university tells you. Okay, so have that much amount of patience. When we talk about sedimentation, sedimentation basically, so let's suppose you have a river which is moving somewhere. Okay, now as the river flow is happening, the river will carry significant amount of sediments along with it, significant amount of materials along with it, which has been eroded from somewhere, carried by the river. Now let's suppose this river gets deposited, or this river deposits certain sediments here. Now after a few years, again more deposits will happen. On top of this, after a few years, more deposits will happen. Now if I talk about, or if I try to visualize the cross section, so the cross section of these deposits will look like what? Cross section will look like something like this, where on the base you will have a separate set of deposits. On top of that, maybe another type of deposits would have happened, right? Maybe in between, few deposits here and there would have been carried out in an unusual manner, and then maybe another set of deposits. That is the cross-sectional analysis of all these deposits. Now, over a period of time, this will exert weight. The materials will exert weight on top of each other, isn't it? They will start applying weight on top of each other. So generally what happens, the lowermost deposit, the particles which are present in the lowermost deposit, they secrete whatever fluid is present, whatever minerals are present under that compression. They will secrete that. And the materials, they start joining together. They start solidifying. And as a result of initially compaction, compaction means what? When you make something compact, what does that represent? You compress it, you press it over. That is compaction, right? As a result of that compaction and eventual cementation, where they join together because of maybe calcium which is present in these minerals, etc. They join together and then they form what is a sedimentary rock system. Sedimentary rock system has always or will always be created as a result of the solidification of the deposits. Now, those deposits can be carried out by the river action. Those deposits can be carried by the marine action, the sea wave action. Those deposits can be carried by the glaciers. Those deposits can be carried by the wind. Regardless of whichever agent of nature we are talking about, these deposits, when they solidify, when they harden, that is when you have the sedimentary rock system. So they get created by the solidification of deposits. Materials. Okay, these deposited materials, they will solidify to form the sedimentary rocks. Now apply your logic here. In the case of lithification, is the same process. Lithification is the hardening and the compaction and cementation. Then eventually when they harden, that is what is also referred to as lithification. Lithification as a term, lith is the term derived of which means rocks. Whenever you talk about lith, right, protolith, right, batholith, phacholith, lith always represents rocks. So it is from that you have the term lithosphere also. So lithification is that stage in the entire process of formation of sedimentary rock where eventually it will harden to create a rock-like structure. Now here, apply your logic. This particular sedimentary rock system, will it have organic materials present in it? Yes or no? What do you think? Very good. Perfect. It will have the presence of organic materials. That is why you will find coal wherever coal is formed. Coal will be found in sedimentary rock systems. You will find petroleum, crude oil, shale, natural gas. That will also be found in sedimentary rock system. Right? So because both of them are produced as a result of organic processes. Coal is produced as a result of the fossilization and carbonification of the trees, the woody trees. They basically, over a period of millions of years, they fossilize to form coal. Natural gas and crude oil is created as a result of fossilization of marine organisms, marine animals. So these marine species, when they die, they get deposited over multiple different substances. They basically change their structure into crude oil and natural gas. So they will be found in the sedimentary rock systems. Okay. Now, because the sedimentary rock systems will consist of a variety of different materials. Just to give you an image of it, those of you who have never seen that. So just because here, if you observe this sedimentary rock system, now this will be very different from an igneous rock system. This is an igneous rock and this is a sedimentary rock. While igneous rock represents a kind of a uniformity all over, observe the igneous rock, it is going to be uniform in appearance. But if you observe the sedimentary rock, it will have a combination of various different types of materials, right? So that is why sedimentary rocks, they are also referred to as softer rocks. Why? Because when you have so many different types of materials, obviously they will be not very strong. All these materials, they will not be joined together with the equal amount of force. They would have simply been accumulated together and solidified, isn't it? So that is why sedimentary rocks break very easily, softer rock strata. Now this is something that you would experience sometimes to a very preliminary level, even in your backyard. For example, sometimes, if let's suppose you have observed or kept a flowering pot ever in your life, in your household, you have seen a flowering pot in which you grow plants, obviously. Now in that flowering pot, as long as you continue to water it, as long as you continue to tend for it, the soil remains good and tillable, fertile, etc. But leave it outside for a few days, leave it outside for a few months, don't tend to it, don't take any care of that soil. Now, after 3 to 4 months, if you go there, if you try to basically remove the soil with your fingers, you won't be able to. It would have hardened. The soil structure would have hardened, very similar to that of a rock, right? So, why does that happen? You will find that if the soil, very fine particled soil, you keep it out in a flowering pot for, let's suppose, 1 year without tending to it, after some time, what you come across is that the particle size has grown slightly larger also. It will develop a sandy like feature. So that is the process where it starts to solidify. It takes multiple years, maybe hundreds of years in certain cases, even thousands of years for the formation of sedimentary rocks, but they are softer rock structures. Okay. Now, then we have metamorphic rocks. Metamorphic. The term is derived from the word metamorphosis. Metamorphosis means what? Change of shape, structure, etc. That is the process of metamorphosis. So the existing rocks, be it igneous, sedimentary, or any other kind of metamorphic, any kind of rock, when it is exposed to high amount of pressure or exposed to very high temperature, in either of these instances, the rock changes its particle arrangement, mineral arrangement, density of the particles, the texture, the size of the grains of the particle, everything changes. And eventually, the rock evolves to be something very different. So, that is what is metamorphic rocks. That is, when the existing rock types, they are exposed to temperature, high temperature or high pressure, they change their shape, structure to form metamorphic rocks. So, existing rocks, when exposed to high temperature and high pressure or high pressure, high pressure, they change to metamorphic rock systems. That is what you observe. For example, limestone. Limestone is a sedimentary rock. Now, limestone, when it undergoes metamorphosis, it produces marble. Marble that you use for construction purposes, etc. So, that is basically An example of it, limestone changes to marble. Right? Granite, igneous rock, changes into gneiss. So you have either the sedimentary rock or the igneous rock or even an other metamorphic rock. When they are exposed to high temperature pressure, they change their state. They not in the terms of they become liquid or gaseous. Basically, the arrangement, the properties of that changes. Okay, so any of the existing rocks can change into metamorphic rock system. Now we will talk about each of these rock systems into a slightly greater detail. So when we talk about igneous rocks, observe the image here first of all. Before looking at the definition and everything, observe the image here. The image that you will observe here, you will find a kind of a uniformity. Right? Each of the particles, they would represent a kind of a uniformity. So what does that tell you? So I always maintain this. You can learn much more from a particular small picture as compared to what you will see in written in multiple different texts in various paragraphs. I don't know how many of you have gotten the opportunity to visit or maybe take a look at few of the books of foreign universities, American universities in particular. You'll find that the method or the mode of inculcation of knowledge in those areas is so very different. For example, when we talk about geography textbooks here, what do we observe? Very bulky. Take any geography textbook, very bulky, very boring, full of text here and there. Take a look at any of their books. You will find that hardly in one page you will find 10 words written, only represented by the images, right? Be it volcanism, be it earthquakes, be it plate movement, everything only represented by images. So that is the approach that we are also going to follow. I will provide you the text also, because we have that innate requirement that unless and until something is written, we feel incomplete. But all the meanwhile, I want you to be focusing on the images. Once you focus on the images and once you start to understand from those images, those pictographic memories, their recollection power of mind is much better when it comes to pictographic memories as compared to the textual memories. So that is why observe the images carefully always. Now, when you are observing this particular image here, there is a uniformity of material. That means a set of material would have cooled down and would have solidified to create this kind of an igneous rock, isn't it? All those materials would have cooled down at the same time to form this igneous rock. But here also, if you will observe here, you will notice that there is no other foreign material which is present. Now, each of the particles, they will have their own grain size. The particles have their own size, right? So they would have solidified from the molten materials. Now, if let's suppose we say that molten materials have solidified, molten materials can solidify in various places. For example, let's suppose this is the Earth's surface. Now, from this region, you have volcanic eruption which happens, and volcanic material or lava spreads over, right? So, this lava, when it cools down, it will form an igneous rock. But also it can happen that somewhere in the interior, this molten material maybe has spread between the layer of the rocks and then has solidified. So that will also be an igneous rock, but it is found to be present in the interior. So based upon where the igneous rock has been created, where the igneous rock has been formed, if it is formed on the surface, it is referred to as volcanic rock or extrusive rock. If it is formed in the interior, it is referred to as intrusive igneous rock. So that is the first major classification. So here, Igneous rock may form with or without crystallization. Crystallization is when the atoms and the molecules, they start forming bonds with each other and they form larger crystals. So each of the grains, they represent individual crystals, for example. Either below the surface, if they are formed below the surface, they are referred to as intrusive or plutonic. If they are formed above the surface, then they are referred to as extrusive or volcanic rocks. Okay, that is the general differentiation that you will find. Now here, when we talk about it, basically, even these igneous rocks, the cooling down will be different. The rate of cooling down will be different. And listen for the next couple of minutes very carefully. When we say that the molten material has solidified to form this rock, so that rate of cooling can be different. Rate of cooling can be fast, rate of cooling can be slow. Now, why should we bother? If the rate of cooling is fast or slow, eventually it will be solid. So why should we bother about it? But understand one basic property here. If suppose I have molten materials here, if let's suppose I have molten materials, and here the rate of cooling is very slow. So if the rate of cooling is very slow, so each of these particles will have enough time to form as many linkages, as many bonds as possible before cooling down into solid. As long as they are molten in a molten state, they will be able to form as much bonds and structure as possible. So the crystal size, the size of individual crystal which will be created, the individual rock grain which will be created, that crystal size will be much larger if the rate of cooling is slow. Because, again, I will reiterate, when the rate of cooling of the molten materials, liquid materials, when they cool down very slowly, they will have enough time, the individual molecules and the atoms will have enough time to form linkages with the other atoms. So each of the crystals and the grain size will be larger. Whereas, if let's suppose the cooling happens suddenly, all of a sudden, the entire liquid cools down to become a solid. That means very rapid rate of cooling. So the particles, before forming the bonds themselves, they will solidify where they are. So the individual crystal or the grain size in this case will be different, will be smaller, isn't it? So that is a major difference that you will find between the intrusive and the extrusive system of rocks. In the case of intrusive rocks, which are formed in the interior, what do you think? The rate of cooling, will it be faster or will it be slower? In the case of when the rocks are formed in the interior, the rate of cooling will be fast, or do you think that the rate of cooling will be slow? Very good. Beautiful. When the rocks are getting created in the interior, the rate of cooling will be very slow because that interior heat is also there, right? No outside atmospheric contact. But when we talk about the extrusive, lava eruption has happened. Very immediately it will start solidifying into rocks because it is in contact with the outside atmosphere. So the rate of cooling is different in the interior as compared to the exterior. That is why intrusive igneous rocks you will find, they have much larger grain size. They are coarse grained. Okay, they will have a larger grain size. So intrusive igneous rocks, here the rate of cooling is slow, so the grain size is going to be larger. Rate of cooling is slow. So as a result of that, the grain size or the particle size is large. Right? So that is formed in the interior. Intrusive rocks, they are formed when the molten materials, they solidify in the interior itself, in the interior portion of the crust, in maybe around the region of moho or in the upper region of the crust, but it has not erupted on the surface. So the grain size will be larger. Whereas when we talk about extrusive, where the lava has flowed out and then has solidified, the process of solidification will be very quick. So these rocks erupt on the surface, resulting in small crystals as the cooling takes place very quickly. Basalt, tuff, pumice, these are examples of extrusive igneous rocks. Now, this is the case of intrusive and extrusive. I hope that is understood, isn't it? I don't think there would be any issues in this up till this point. Okay, good. Now, there is further classification which is done for the igneous rocks. And this classification is done based upon the minerals which are present in the igneous rock. Minerals which are present in the igneous or any kind of rock system, the minerals which are present, they are very, very important and relevant in terms of imparting the, let's say, magnetic property, density, and other factors to the rocks. So, we will study this in detail when we come to the next module of earthquakes and volcanoes. But here, let me give you a preliminary idea. Based upon the type of minerals present, you have the classification of these igneous rocks into felsic, mafic, and ultramafic. Based upon minerals present. Felsic, rich in silica. Right? It will be brighter in appearance, lighter in density and weight also. So this will be brighter in appearance, less density. Okay, that is something you will find as a characteristic of felsic rocks. Then you have mafic. Mafic, here mafic basically stands for, Ma stands for magnesium, Fic stands for iron. So it is rich in magnesium and iron. Rich in iron and magnesium. So it will be darker in appearance, much heavier density, and thereby the weight will also be higher. So here, darker and denser. Okay. And then we have ultramafic. Ultramafic, even greater proportion, around 70 to 75% of that is dominated by iron and magnesium only. So that will be somewhere around greenish in appearance that you will observe. So this is the general classification. I will tell you about the difference in melting points of all these lava and magma also as we come to the portion of volcanoes and we study about the chemical properties of magma. There I will make you aware about the melting point, etc. also. But this is the classification of igneous rocks. So very quickly, if I have to recap it, so igneous rocks classified based upon where they get created. If they get created on the surface, extrusive. If they get created underneath the surface in the interior, intrusive. Intrusive means what? The process of cooling down is going to happen very slowly. So when the cooling down is happening very slowly, the particles will have enough time to combine with the other molecules, other particles, and form a larger crystal. Right? So grain size in the intrusive igneous rocks, that is always going to be larger. Larger crystals will be created because the rate of cooling is slow, allowing particles enough time to combine with each other. When you talk about the extrusive ones, which are created on the surface, there the grain size will be very small because the cooling is happening almost instantaneously. So the individual molecules, they don't have much time to combine with the other molecules or form bonds with the other molecules. So that is why the grain size is particularly smaller. Based upon the minerals which are present, felsic, mafic, ultramafic, felsic, it is going to be very light in density. It is going to be brightish in appearance, grayish appearance, or generally off-whitish appearance that you will observe. And it is rich in silica. That is why it is lighter in weight. When we talk about the region of mafic, so that is rich in iron, magnesium, darker appearance, the blackish appearance, and then eventually ultramafic, greenish in appearance. Density will be higher. Okay. Now here you have this as the basic classification. Then after that we have the sedimentary rocks. Now sedimentary rocks created as a result of the solidification of the deposits. Now based upon how these deposits have been attained, you have the further classification of sedimentary rock which is attained, that is the clastic, the organic, and the chemical sedimentary rock, based upon how these deposits have been attained. Because we do know that it is these deposits which make up the solidification of the deposits, make up the sedimentary rocks. But how those deposits have been attained? For example, if you consider the types of sedimentary rocks, you have the clastic sedimentary rock, you have the chemical sedimentary rock, and you also have the organic sedimentary rock. If you take a look at it here, organic sedimentary rock, they are formed. So take the case of coal. Now, coal we have seen is formed as a result of the compaction of the various woody trees and the woody plants. When they get compacted, coal is created. Coal is formed. Right. Now, that is an organic process. So, it is an organic sedimentary rock. When you talk about, let's suppose, rocks such as sandstone, siltstone. So, the name in itself tells you sandstone. Formed out of what? Deposits of sand. Over a period of time, that deposit of sand would have created that sandstone. Siltstone. Siltstone is what? What is silt? Silt is the deposit made by a river. In the river channel, you will observe that grayish deposit which is happening. That is basically silt. And that silt, by the way, is very fertile. But over a period of time, when that silt solidifies, it accumulates, it forms siltstone. Then we also have chemical sedimentary rocks, where the sedimentary rock formation in itself is a product of the chemical reaction. We'll talk about it, but we'll talk about it after the break. So we'll further talk about it after the break, and then we will continue. Okay. Are these igneous rocks ores? Ores can be found. So what do we mean by ore? Any particular larger rock from where a mineral can be extracted. So sedimentary rocks can also be ore. Observe this, iron ore is a kind of a chemical sedimentary rock. For example, when you talk about pegmatite, from that mica is extracted. So that can also be an ore. So ore is, even metamorphic rocks are act as ore sometimes. Sedimentary rocks can also act as ore sometimes. Sedimentary rocks, Gongala, are basically those kind of rocks which are formed as a result of deposits made by the rivers. When they solidify, that is what we have as sedimentary rocks. Siltstones are soft rocks, yes. You want me to go slow, is it? Okay. Because we are in the third class, my dear friend. And till now, we have not completed the portion even up to the second class. Please understand, these are very minor portions that you are confronted with. The theories, etc., they are still left over. So if we slow down here, you can think about it that by the end of, when we come to the portions such as climatology, etc., that will be almost incorrigible. Or what we will do is, if we slow down right now in order to finish, we will have to eliminate some portions which are not relevant, which are not that particular important. So thank you, Vishwas. I hope that is helpful. Shazia, please continue your class, and at the end of any topic, pick all questions. This will work better because students might not pause to ask questions. Okay. See, you know what happens. Now I have taken enough number of classes to understand this trend or a pattern. Generally, what happens is that suppose I am a student, if I face a problem, immediately I will start flooding the comment section and the doubt section that how come, what are you saying about intrusive, extrusive? Please repeat. Please tell me, otherwise it simply doesn't make sense to me. And we will be flooding those questions. But let's suppose I answer your question, and then in the meanwhile someone else has asked what is sedimentary rock and what is mafic, ultramafic. Once your question is quenched, always the tendency of the candidate is, why don't we move faster? Unless and until your question is taken care of, the tendency is, why don't we go slow? Don't worry, we have enough experience of how to conduct classes. We will continue with the conduction of the classes. Just ensure that you're at your end, you are able to perceive, you are able to understand. That should be the purpose. If you are doing that, if you are fulfilling that, leave rest of it to our end. We will conduct the classes with the required pace. We need to carry all the students together. Chances are many of the students who might be finding this particular portion to be a bit difficult, chances are they will find climatology to be very easy and conceptual. And in that case, God forbid, if you find the portion of climatology to be difficult and the other students, if they push that move forward, then that will be a predicament that you won't want, would you? So that is why don't worry about the other externalities around the class. How do we tackle the questions? When do we tackle the questions? Do we take up these MCQs or not? If this content should be written in this manner or that manner, leave it to us. At your end, you just ensure that you follow what is being taught in the class. Okay? So that is where we will basically in okay, Chandrajyoti, just follow the portion of that we have covered here about the type of the igneous rock. Okay, right? And we'll take a break. We'll take a break till 8. Right? That should be perfect. I will talk about what is clastic again when I come back. So, do you want it more? Okay. 15 minutes break. Okay. So 8:05 a.m. See, the major demand is 15 minutes break. That is why, because it is the first week. So I don't want to be turning out to be a harsh. So let's take a break and let's be back. A confirmation about the audio, please. If the audio is clear and available. Thank you. And thank you for all the suggestions about where we should do what for the lecture. Okay. Again, I will reiterate, please just ensure that you are able to understand at your end. Leave the lecture to our side. Okay. So, Vishwas and all of you, whosoever are giving such suggestions, thank you and very well received. So, now we talk about these sedimentary rocks and basically the types of these sedimentary rocks. So, when we talk about the types of sedimentary rocks here, these sedimentary rocks are created by what? Solidification of deposits. Deposits which have been created by river action, glacier action, wind action, etc. Sometimes what also happens that let's suppose you have an existing rock type. Let's suppose mafic rock basically, Shreyansh is when we say mafic rock, mafic is magnesium and iron. So magnesium and iron, when they are dominant, they are referred to as mafic rocks. Generally, the melting point in those particular lava is also higher. They will have higher density, darker appearance, and the presence of iron and magnesium is close to around 50% to 55% in that case. Okay, right? Now, sometimes when we talk about the sedimentary rocks, geographical north and south pole are different from the magnetic north and south pole, Shalu. They are different. Let's suppose this is your sedimentary rock. Now, due to heat, due to cold conditions, maybe due to excessive rainfall, etc., this rock develops certain kinds of anomalies. Okay, or it weakens in structure due to exposure to greater amount of heat, cold conditions, cold temperature, etc. It basically weakens in structure and it breaks into multiple smaller parts. Now these smaller parts can be carried if, let's suppose, there's a river moving nearby. The river will carry these smaller parts, isn't it? They will deposit it somewhere. Or might even be possible that you might have in a region a waterfall. Let's suppose that waterfall is falling upon a particular kind of a rock. It has broken some particles and fragments of those rocks and has deposited them furthermore. So these sediments which have been deposited why? Because of the mechanical breakage of the rocks. There has been a mechanical force in place which has broken these rocks into smaller components and then created those deposits, isn't it? So, such kind of rocks which get created due to the mechanical breakage and then the deposits are made, those are clastic sedimentary. So, when we say clastic sedimentary, these rocks are formed from the mechanical weathering debris. So, basically, an existing rock type, maybe an igneous, sedimentary, or a metamorphic, any existing rock type, when exposed to the mechanical pressures and the mechanical forces, when they break and they create deposits, those deposits, when they solidify, they will be clastic sedimentary. For example, sandstone is formed by the solidification of, in certain areas, if you have deposits of sand, when they solidify, you have the formation of sandstone. If let's suppose there's a river action, there's a river which is moving, and there the river deposits those silts, and that silt solidifies, that creates a silt stone. So, like that, you basically have the clastic sedimentary rock. It is an outcome of the mechanical process of breakage of the rocks. Now, here then comes the chemical sedimentary rocks. Chemical sedimentary rocks basically, as a result of chemical action, you have the creation of these deposits. What do we mean by that? That as a result of chemical action. How can chemical action create deposits? So here, the example can be taken of that of iron ore. So, for example, what are examples of mechanical forces? Examples of mechanical forces you can take as, for example, a river which is moving, it is hitting the rock continuously, so it will break that rock. Mechanical force will be there. Heating by the sun is again, it will weaken the rock. Expansion, contraction of the rock will break the rock. So, any of these kinds, they are mechanical forces. Now, let's suppose we talk about the formation of iron ore. By the way, again, nobody is going to ask you in the examination that describe the formation of iron ore. This is just for your own understanding. So, iron ore initially was formed in the region of shallow seas. Shallow water. Shallow water means which is not very deep. Now, in these shallow waters, you had the presence of iron, iron particles which were dissolved in water. Right, iron particles which are dissolved in water. So very much a part of the liquid water itself. Water has various minerals. Water sometimes has calcium dissolved in it, sometimes has sodium dissolved in it, sometimes has iron dissolved in it, etc. So water has got various particles. So like that, iron was also one of those particles which significantly is to be found in almost all the oceanic areas. In the sea regions also, some amount of iron is dissolved. Now, because you are considering about shallow waters which are not very deep, here underwater plants also start to grow. Now, when the plants grow, plants produce food by the process of photosynthesis. So the plants, they carry out the process of photosynthesis. In the process of photosynthesis, they will consume CO2 and they will produce oxygen as a byproduct. Okay, they will consume CO2 and they will produce oxygen as a byproduct. So here there was a reaction of oxygen plus dissolved iron. Okay, oxygen and dissolved iron. So basically here you have iron which reacts with oxygen to form iron oxide, ferrous oxide, and this basically is in a solid state. Okay, so that is how it is getting deposited. So this solid state, that starts getting deposited. Eventually these deposits will be quite significant, and that is how iron ore gets created. But this creation of iron ore or the creation of this deposit would not have happened if the chemical reaction would not have taken place. So that is why it is an example of a chemical sedimentary rock. Similarly, when we talk about limestone, limestone is formed how? So when again, limestone is typically to be found in those areas which have remained underwater in past, in history. Some or the other time they would have remained underwater. For example, in India, you find limestone in the region of Madhya Pradesh. You find limestone in the region of Meghalaya. You find limestone in certain areas of Karnataka, Andhra Pradesh also, some parts of Tamil Nadu also, Rajasthan. So historically, those areas which have remained underwater, in those areas limestones are created. And it is in shallow seas where basically the shell-bearing animals, such as the crustaceans, the mollusks, such as the crabs, those animals which have shells around them, when they die, while the body decomposes, the shell is left behind, and that shell is rich in calcium carbonate. It is abundant in calcium carbonate. Now, over a period of time, many of these deposits, they get on top of each other. They are compressed by further other deposits, and you have creation of the layers of limestone which gets created. And eventually, as the geomorphic cycles goes on, as the land gets uplifted or as the land further sinks, many areas, they get uplifted and they are rich in limestone. So that limestone where the enrichment of calcium carbonate and magnesium sulfate and carbonate happens. That is also a chemical reaction. So this is also formed underwater. So thereby you can see that the classification of the sedimentary rock is done on the basis of how these deposits have been created. Whether the deposits have been created by a mechanical force, clastic sedimentary, whether it has been created due to chemical reaction, chemical sedimentary, whether it is because of the organic deposits, let's say the trees, etc., they have been deposited in a region, they have been fossilized in a region. That is what you have as the organic sedimentary, example, coal. So this is the basic classification of sedimentary rocks. In the water, how CO2 consumed? Are we aware about the fact that water has got dissolved carbon dioxide and dissolved oxygen as well? I hope we are aware that water has got dissolved oxygen, because that is what the organisms use in order to carry out their respiration. And I hope we are also aware that one of the richest source for the consumption of carbon dioxide across the planet is the oceans. The oceans overall, they consume close to around 30 to 35% of the carbon dioxide which is present in the atmosphere, that is consumed and is absorbed by the oceans directly. So carbon dioxide in the dissolved state is found to be present. Otherwise, you would not have come across a situation of underwater, or in areas where you have underwater plants, etc. You would never have come across those, but you have those. Okay, right? How the second rock type, that is chemical sedimentary rock. Chemical sedimentary rock, they are classified based upon when chemical reaction, any chemical reaction that is instrumental in creation of those deposits, and those deposits when they solidify, that is a, okay, let me do one thing, something which is easily consumable. Sedimentary rocks. Chemical reactions are instrumental in formation of deposits. Deposits solidify to form rocks. As simple as that. Chemical reactions, for example, underwater, dissolved oxygen and dissolved iron, they get together to form iron oxide, which is in a solid state. So that will be the deposit. These deposits will solidify to form iron ore. Is that understood? I hope that is understood. Now, we come to the metamorphic rocks. So, metamorphic rocks, what do we understand by metamorphic? So, any of the existing rock type, be it igneous, sedimentary, or other metamorphic rock systems, any of the existing rock types, whenever they basically are exposed to very high temperature or very high pressure, in either of the instances, whenever they are exposed to either a very high temperature or a high pressure, that is when the rocks, their nature, the arrangement of the particles, etc., that changes quite considerably. And you will observe the formation and the creation of metamorphic rocks in the process. Okay, so metamorphic rocks are formed by being deep beneath the Earth's surface, subjected to high temperature and great pressure of the rock layers above. Okay, or even in the mountainous areas also. So many of the times, as you will study later with the understanding of the plate tectonics, that in many of the regions you will observe that the existing crust goes underneath into the region of mantle, and the portion starts melting up, right? So there also high temperature is exposed. So rocks can basically change their state, change their nature, change their property. Now, this metamorphic rock is also classified into different types based upon the appearance. For example, certain rocks you will observe, they appear as a like a banded structure. Observe here, it will appear as if there are bands, right? So, accordingly, the classification of metamorphic rocks is into foliated and non-foliated. Foliated means it will have development of separate bands, and non-foliated a uniform structure. So just by appearance sake, what is it that we can conclude about this? For example, in the case of foliated rocks, can we say that these foliated rocks, they have the presence of various different minerals in them? We can say that, right? That they will have different minerals present in them based upon the color appearance itself. We do know that whatever is present here is very different from whatever is present in the brighter portion, is very different from the other area. So, when in a particular rock you have many different types of minerals, and then they are compressed or applied pressure to in a kind of a non-uniform manner, for example, now or whenever they are applied pressure to in such a manner that different materials, they expand, and due to that exerted pressure, they experience the banding of that happening. So let's suppose you had a particular rock consisting of various different types of minerals. Okay, now if you compress it, let's suppose this undergoes natural compression, so obviously these minerals, they will get expanded here also, here also, here also, here also. Chances are over a period of time you can come across a rock structure which will be having a kind of a band like pattern. These would have expanded. So such kind of a rock or a metamorphic rock is a foliated, having a banded or a layered like structure. Example, you can have the example of gneiss, right? Schist, etc. These are examples of foliated rocks. Whereas non-foliated, let's suppose uniform rock type, and also if there is exposure to high temperature, in that case you won't have this kind of a banding created, right? You will have a uniform conversion of rock into metamorphic rock. So such are known as non-foliated. Example, marble is an example of non-foliated. Okay, so when we talk about the types of metamorphic rock, they are classified into foliated and non-foliated. Foliated rocks, they are produced by the exposure to heat and pressure, which makes them appear layered. So phyllite, gneiss, schist, these are examples of foliated metamorphic rocks. Whereas when we talk about marble, quartzite, these are examples of non-foliated. They will give you a uniform appearance. Okay, so this is the general classification of that. Now, we know igneous rocks, we know about sedimentary rocks, we also know about metamorphic rocks, the basic of it. Now, on top of that, we have to understand that each of these rocks, they have the ability to get converted into another rock type. For example, an igneous rock can get broken into smaller parts by the river action, by the force of the river, and those smaller parts can get deposited somewhere, create a sedimentary rock. A sedimentary rock can be exposed to very high degree of pressure, can get converted into metamorphic rock. A metamorphic rock can get broken into smaller parts, can get converted into sedimentary rock. Either a sedimentary or igneous or metamorphic rock, they can get subducted underneath the earth's crust. They can melt and then again come up as a volcanic eruption to form other igneous rock. So basically, each of the rock type, provided the suitable conditions of temperature and pressure, they have the ability to get converted into another rock. They continue to keep on getting recycled from one rock type to the other rock type. They continue to get recycled. And that is what creates the rock cycle. That is what is the concept of rock cycle. So, in the case of the rock cycle, you will observe that provided the suitable conditions of temperature, pressure, or whatever might be the suitable condition, igneous rock can get converted into any of the types, metamorphic rocks can get converted into any of the types, and so can sedimentary rock system. For example, let's take the case of a metamorphic rock. Now, this metamorphic rock, if it breaks down due to mechanical weathering or erosion activities by the rivers, glaciers, anything, they can break it down. Now, when they break it down, they will create sediments. Now, those sediments, after compaction and cementation, can lead to sedimentary rock formation. That sedimentary rock formation, again, can undergo weathering and erosion, again, lead to the formation of sediments. Again, those sediments can harden to form sedimentary rocks again. Now, those sedimentary rocks, when exposed to high temperature and pressure, they can get converted into metamorphic rocks. Right? Then, igneous rocks, if you consider, if they are exposed to weathering erosion, they will have smaller particles. Just a moment. So, here you will find that they have smaller particles. They get eroded, weathered into smaller particles. And these smaller particles, they again create those sediments. And those sediments again can get created, or they can form the sedimentary rock cycle overall. So, like that, each of the rock types can get converted into other one. Metamorphic rock, let's suppose, when they are induced to melting, let's suppose that you have, as we will study later, sometimes what you have is that one of the rocks, they basically, or the crust, simply undergoes subduction. So when the crust undergoes subduction, upon reaching a particular depth, it starts to melt. And the molten material then rises up in the form of another volcanic eruption, and it spreads over. Right? So when this lava then spreads over, it will again form an igneous rock. Earlier situation might have been igneous, metamorphic, or sedimentary, but again it will create an igneous rock. So just like that, metamorphic rock, when it undergoes melting, it will form magma. Magma will solidify to form igneous rock. It might be possible that that magma again, let's suppose, gets subducted, or that igneous rock gets subducted, again melts, and again this process is repeated. So provided the suitable conditions of temperature, pressure, mechanical forces, etc., each of the rock type, they can change their state from sedimentary to igneous to metamorphic, and vice versa also remains true for all of these cases. Okay, that is the case of rock cycle. This is something that goes on across the entirety of the world, where you will observe that igneous rocks, they are created first whenever you have a volcanic eruption. Now that can get eroded, or on top of that you can have more igneous rocks getting created. So the lower ones, they get converted into metamorphic. Now they can get eroded, form sediments, they can form sedimentary rock systems. Sedimentary rock systems can get metamorphosed. So that kind of a continuous cycle is observed all across. Okay. Now, after this, we come to volcanic eruption, magma, lava. We will study in detail. Don't worry. We come to the portion of origin of continents. Very, very important for your portion of geomorphology. In fact, you can argue this is where you start the study of actually what happens on the land surface and how the land surface actually changes form. So, in this area, we will be studying about the continental drift. We will study about the seafloor spreading. Kanchan, foliage rocks are very different from foliated rocks. If you are asking about foliated rocks, that is when multiple minerals are present and they get compressed to a varying degree so that they appear in bands. So foliated and foliage refers to the plants that you have. That is what is foliage. Foliated means the presence of layers. Onion, for example, onion that you would have seen, that is foliated. It has got various different layers associated. Okay. So that is why I have basically asked about it, because here you will observe the answer that is given out. Uh, Acid and basic rocks. Atharv. Acidic and basic, this is the classification of igneous rocks based upon the concentration of silica. It is the presence of silica which denominates whether they are classified as acidic or basic, but that is not a characteristic which is used quite significantly for that differentiation. But nonetheless, when we'll cover the chemical properties of lava, chemical properties of magma, we will talk about the how the concentration of silica, if the presence of silica is high, it is felsic, etc. We will talk about acidic, basic there itself. There's not much importance to that. Then before that, we will also study convection current. Pebbles are basically smaller portions of rocks. The rocks, when they break over, then you have the smaller pebbles created. So when a large rock breaks over, it is not like a cake cutting ceremony that exactly 12 small portions. When two large portions break, you will have multiple small granules also separating. So that is what creates gravel, pebbles, etc. Okay. Convection current theory. And eventually, all of this helped us to understand plate tectonic theory. These are the portions that we shall be covering here. Now, out of this, you will find that plate tectonic is the most relevant one for your mains, along with continental drift and seafloor spreading. This has been asked in the mains examination earlier as well. This is going to be relevant for your mains. Whereas in the prelims, you generally get questions from the area of plate tectonics. Okay. So here we study about the origin of continents. And by this, what do we mean, origin of continents? Are we going to talk about the formation of Africa, formation of Eurasia, etc.? No. Here, when we say origin of continents and oceans, basically, for a long period of time, ever since mankind was able to explore the world and draw its cartographic map to the accuracy, one puzzle which always intrigued everyone is that why is it so that the continents and oceans have these shapes? Why is it that we have mountains? Why is it that we have chains of islands which are present? Why is it that certain areas they have the presence of certain kinds of minerals? This was a question which was always dominant in the mindset of the geographers and the geologists. Now, due to lack of enough scientific data, everybody would postulate their own theory. In the 1800s, especially in the late 1800s, you had a group of people who were referred to as contractionists, right? You had a group of people who were referred to as contractionists. Contractionists, basically, they were referred to this because they adhered to the principle of contraction, in the sense that they talked about the fact that, look, Earth as a planet is cooling down. As compared to the time of its formation, it is cooling down. And because the planet is cooling down, so that is why as it cools down, it will develop wrinkles on the surface. Certain areas will have depth, certain areas will have height. And that is why we have mountains and we have the deep basins and the deep valleys. Now, because these were very famous geographers of those time, their ideology was readily accepted. And also, their theory was readily accepted and virtually remained unchallenged for more than 50, 60 years. It all changed with Alfred Wagner. Alfred Wagner basically was a German meteorologist, an individual who specialized in study of change of climate, that how over the past history Earth's climate has changed. And he would carry numerous studies in the region of Greenland. He would virtually go to the region of Greenland, sail to Greenland, and he would take out deposits of ice and snow. I hope we are aware that deposits of ice and snow, they give you an idea about the climate which would have existed when the snow got deposited. Even the rings around the tree, what is referred to as the process of dendrochronology, that also helps you understand the climatic conditions which would have been prevalent in the past history of the tree by studying the trees and the rings that the trees have. So that is what Alfred Wagner was specializing in. He basically was studying the change of climate that planet has experienced previously. Having said that, as the story goes, one fine Christmas evening, on the eve of Christmas, before Christmas rather, on one fine Christmas Eve, his friends visited him, and one of his friends gifted him a detailed world map. Now, presently, you might trivialize it that world map is present even in the back of my book that I don't even pay attention to. World map is stuck on in front of my wall, on which I basically can scribble it around. I can throw waste on that. But understand, we are talking about more than 100 years back in the early 1900s. So at that point of time, obviously, you did not have the availability of accurate world map. That was a rare collection. So when that was provided to Alfred Wagner, few of the things intrigued him. He was puzzled. And he was puzzled by what? He was puzzled by the fact that the shape of the eastern portion of South America appears to be very similar to the shape of Western Africa. The shape here appears to be very similar to the shape that you observe here. The shape that you observe here is very similar to the shape that you observe here. Now, Wagner was almost convinced significantly that this all cannot be simply mere coincidences. It cannot be possible that all of this is a coincidence that all these places have the same shape. He was very convinced. But then he was intrigued, he was puzzled. He wanted to find the answer to the question that if this is not a coincidence, why is it that these continents have these shapes? Now, because he was an individual who specialized in study of climate, he did not know much about the ground surface, about the continental landmass, oceanic mass, etc. He did not know much about it. So he studied the work of the other geographers to see that whether he can find out his answer in that, but he could not. In the meanwhile, while browsing through the different studies which had been carried out, mind you, we are talking about the early 1900s. So majority of the study by the botanists of the world and also the paleontologists who would study the fossils of older fossil remains, etc., the geologists, they had carried out their own individual study across the world. Now, Wagner started looking at all the data to understand about this unique coincidence. When he was looking at the data, he came upon something which was very unique. All the evidences that he looked for, the evidences pointed to the fact that all these regions, all these land masses, they would have been one. They would have made up a large, unified landmass. And over a period of time, that landmass would have been divided and the continents would have moved. Now, think about it. This is a theory being provided in the early 1900s by an individual who specializes not in the land masses but in the climate. And that individual has got the guts to tell you that look, the land that you are standing upon, that land is not fixed, that land is moving. What will be the impact? Even today, if you think about it, many of you, You have some preconceived notion about the rocks, about the sky, etc. If I tell you something to the contrary, immediately you come back now that you are talking rubbish. I have seen this present here in that book, I have seen that written in that book. It is something your mind is not ready to accept, and that happens. That is not natural human behavior. So even at that point of time, Wagner's entire postulation was looked at with great suspicion. Plus, to add on to the fact, Wagner was a German, right? And basically the entire community, the German scientific community, that was eyed with great suspicion ever since the First World War. Now, all this detail and the theory that he postulated, that was published in an essay which Wagner published in the early 1912s. But it was published in German. The translation for the rest of the world was made available maybe around a decade and a half later in the 1920s. That is when the world for the first time analyzed his information. Now they read about continental drift, that the continents indeed can move, continents indeed can drift. While they were very puzzled by it, they were not ready to accept it. They wanted to look at the reason that Wagner has provided, that why the continents are moving. If you are saying continents are moving, why are they moving? But the reason that Wagner provided, obviously because you don't have an expertise, you cannot provide adequate reasons for that. Those reasons were ridiculed. You had multiple science conventions held in United States with the prime aim of ridiculing the work of Alfred Wagner. And much of it was because of his German background. You had the entire geographical community divided into drifters, so called, and the non drifters. Drifters who would believe that the land would drift, and non drifters who would believe that the land is stable as it is. You had geographers putting forward very weird logics in order to defy what Wagner had said. His theory was rejected. He was ridiculed. He was banished from the geographical community, but he continued to do his own work. And his own work was that of climate research. He continued to do that. It was during one of these voyages to Greenland where Alfred Wagner finally perished. He died. At the time of his death, he was not a very popular person. He was a person who was made fun of. The scientific and the geographical community particularly took great amount of effort to ensure that Wagner was made fun of. At that point of time, Wagner did not have the scientific evidences to back his claim. He did not have the scientific research to back his claim. All that he had was a few set of evidences which indicated that yes, the continents would have drifted, but not the exact reason of it. Later on, the scientific data pointers developed. Almost 50 years later, Wagner was proven correct that yes, indeed, the continents are drifting. It is a different matter that the reasons that were provided by Wagner, they still are incorrect. But the main theory that he provided, that the continents are drifting apart, that was correct. And that was provided by the plate tectonics theory. If you sometimes get to study about how there is geopolitics which plays out even in the scientific community, you will be puzzled by it. The theory of plate tectonics, which is renowned, which is accepted across the entirety of the world. Now, that was accepted very immediately. It was provided by people who were working in US, right? Now, all those US universities, they were working in that. Not to say that they were providing a wrong evidence or a wrong theory of plate tectonics. They, based upon adequate research, they provided the plate tectonic theory. They did not provide reasons why this plate tectonic is happening. It was developed over a period of time. But they provided that this is the theory, this is happening, the world is moving. Everybody accepted that. But when Wagner tried to do so, it was made fun of. It was ridiculed. You will find numerous such instances of scientists, Russian scientists, German scientists, who had made these contributions, but who were largely ignored. But the US based scientists, so this is a different geopolitical context altogether. We don't have to get entangled in that. But the fact of the matter is that the plate tectonic theory that is acceptable today stands on the strong base pillar provided by Alfred Wagner. He could not support his theory, he could not justify his theory, but he had the guts to think about it for the first time. The person who develops an airplane now, that person is a great individual. But the person who, for the first time, had that thought that we can develop a device which can fly, that is a pioneer. That is an individual that you have to value. So is the case with Alfred Wagner. So, with that backdrop, we have to understand what is this continental drift theory. So, basically, the theory in itself is very simple. The theory in itself is about the fact that, let's suppose, you had the planet Earth. Now, Wagner said that at one point of time, planet Earth basically had one large supercontinent. All the land masses were combined into one, right? One large supercontinent. And he named that supercontinent as Pangea. And then he said that the planet was surrounded by water body from all sides. And that is what he named as Panthalassa, or ocean of the world. He went forward to even quote that it is this Panthalassa which is present in the today's Pacific Ocean that you observe, that is a part of the ancient Panthalassa. Having said that, he further postulated that look, this continent basically broke down. This supercontinent broke down, where you had land masses in the northern portion and land masses of the southern portion. So the supercontinent broke into two parts. One was Laurasia or Angara land, which included the lands of Eurasia and North America. This would include Eurasia and North America, this entire region and North America. This would be included in Laurasia, along with Greenland, obviously, and then Gondwana land. Gondwana land, basically consisting of continents of South America, Africa, India, Australia, Madagascar, Antarctica, all of them taken together, that would represent Gondwana land. And he further postulated that this would be broken down furthermore, and due to the drift and the movement of the continents, this would be further broken down to have the present day origin of the continents and the oceans that you have. The present day arrangement that you observe of the various different continents and oceans, that has been created because of the drift induced. And that is why you have the various different land masses in the shape that they have, in the shape that you see. Okay. So that was basically the postulation, that the present day land masses and the land and ocean has been derived because of the drifting of the continents and the oceans. Now, in order to support this theory, he provided various evidences. Now, evidences were to the point. Now, let us first of all take a look at what are the evidences that Alfred Wagner managed to provide. So, amongst the evidences that you will observe, you have a significant evidence in the form of geological evidence which are present. Laurasia basically included regions of North America and Eurasia. Okay. Now, the first evidence that he provided was a jigsaw fit of continents. I'm sure most of you would have played with jigsaw puzzle in your life, in your younger days, in your childhood days, where when you are 3 years, 2 years, 4 years old, you basically get those jigsaw puzzles you have to arrange in order to take a look at the larger image. Right. So everything appears to fit with respect to each other. So something very similar is what you observe in the jigsaw fit of the continents as well. So here, The eastern coast of South America has got a greater resemblance with the western coast of Africa. The resemblance is quite significant. Now, this cannot be a sheer coincidence that land masses which are thousands of kilometers apart, they have the same shape. Similarly, when we talk about the eastern coast of Africa to the region of the Arabian Peninsula, there also the shape is very similar. Western coast of India and the shape of Madagascar, that also is very similar. So all of this cannot be a sheer coincidence, can it? So all of this indicates to a reality that sometime in the geological past or history of this region, all the land masses would have been together and they would basically have been broken down. They would have been divided, further ruptured to create the present state. Right? So that is what the expectation was. That is what the theory was also about. Now, other than that, there were other geological evidences. For example, when he looked at the rock systems here in the eastern part of North America and the type of rocks which are found in the region of Scotland. Now, understand, these are separated by tens of thousands of kilometers. But he found out that these both rock types, they have the same origin, they have the same property, they have the same features associated also. So, again, can it be a coincidence that rocks which are separated by tens of thousands of kilometers, how come they will have the same property, the same physical properties, etc.? How can that be possible? It simply cannot be, can it? So that means these regions would have been together when the rocks would have been formed. Similarly, he observed that the rock systems in the eastern part in the region of Brazilian highlands has a greater resemblance with the rock systems in the part of Western Africa. How can that be possible? It can only be possible if they would have been together. Right. Rock systems in South America had a great resemblance to the rock systems in the region of South Africa also. So that also indicates that they would have been together. So all these evidences, they indicated that the region would have been together. So similarity of geological structures across continents, so presence of similar mountain ranges across North America and Europe. Example, Appalachians of North America are similar to the Scottish Highlands. Similarity in geological rock structure in Western and South America also. Western Africa and South America also. Now, other than this, you also had basically the evidence of placer deposits. Placer deposits. What are placer deposits? So let's suppose you have a mountainous area, a mountainous region rich in some or the other minerals. Now let's suppose here in the mountains you find a deposit, significant large deposit of gold. I hope we are aware that gold is not soluble in water, right? Gold is insoluble in water. Now, let's suppose here you have a river system which is moving in this region. Now, as this river moves, very slowly but steadily so, it will start plucking the gold from here. The gold will be carried by the river system, isn't it? And the river might deposit that gold somewhere downstream. So here, the deposits that you see have been placed very far away from where the source rock was found, isn't it? So these are the deposits which are referred to as placers or the placer deposit. These are known as placer deposits. And these are known as source rocks. Now, once we know what these placer deposits are, here, if you look at the map again, Now you have significant amount of gold deposits to be found in the western portion of Africa. Substantial amount of gold deposits, which are placer in nature, which are placer deposits. But then the source rock could not be found in Western Africa. Regardless of how much the geologists worked hard, they could not find the source rock for these placer deposits. To the surprise of everyone, the source rock was found where? In the region of Brazil. So again, how can it be possible? How can it be possible that you can have a source rock in the region of Brazilian highlands and a placer deposit far away across the Atlantic Ocean into the region of Africa? Simply incomprehensible. That can only be possible if these two would have been together at some point of time in history and then would have separated. Isn't it? So look at how all the evidences are pointing to the oneness of the landmass. So here, placer deposits. So placer deposits of gold found in West Africa. Africa had the source rocks in the region of Brazil. Brazilian highlands. Indicates the land would have been together. Placer deposit, is it understood? It is just a geological evidence, just another geological evidence. Good. Is it possible that continent happened due to expansion of planet that we learned yesterday? Yesterday, did we learn about the expansion of planet? Which, please enlighten me, Devyani. This is a bit scary. When did we study about the expansion of planet yesterday? I have read mantle is also consisting of seema and oceanic crust also seema. Please clarify. See, SEMA, that classification again is not used. That SEMA classification is given of the 1850s by Edward Hughes. So at that point of time, when the theory was provided, he said mantle consists of SEMA. Then nowadays it is few of the school books you will find that oceanic crust is referred to as SEMA. You cannot virtually classify that okay, this region is only Sial, because magnesium you find, iron you find even in the continental crust, right? Then you will find other elements even in the oceanic crust. Mantle, you will find different types of material. So that classification is no longer used. If you have to still use it, you can talk about the fact that you have the classification of the continental crust having Sial, oceanic crust as a having SEMA. What you are talking about as mantle consisting of mantle having SEMA, the topmost having Sial and the bottommost having Nephi. That is the classification provided in the 1800s by the Austrian geologist with the name of Edward Hughes. So don't worry about it. Okay. He's talking about expansion of universe. See, please understand, the earth never expanded. Ever since the time of formation, the earth never went for an expansion. And yesterday, whichever things that we studied about the evolution of planet Earth, now that evolution was something that we studied billions of years ago. These placer deposits, etc., they would have been created many billion, maybe couple of billion years later after the, or even much later than that. Okay, so this is nothing to do with the time of the origin of the planet Earth. How was the source of the placer deposit accurately discovered? Radiocarbon dating, yes. Expansion of universe that we studied was a very different matter. That expansion of universe doesn't mean that the individual elements are increasing in size. It simply means that the all the different components, they are moving away from each other. That is the portion. So this is very different from that concept. This is not at all related with that concept. Okay. Okay, Alfred Wagner, the name. Alfred Wagner was the name who was the individual who provided continental drift theory. Okay, and he is also referred to be the father of the theory of plate tectonics, in the sense that his theories eventually led to the modern day understanding. Then Alfred Wagner basically took the pains to look at other set of evidences also. And the evidences, one of those evidences was the impact of the glacial movement. So you had the glacial evidences. Glacial evidences. Now, I hope we are aware, even if we are not aware, when glaciers move, we are talking about millions of tons of ice which move against the surface. Millions of tons of ice. So the weight imposed is very high. They are as massive a force as nature can impose on the ground. No other agent of nature will have that much force as a glacier exerts. So wherever a glacier moves, it not only scoops the ground surface, it creates certain features which are very unique to those glaciers. And it also carries out very fine. So think about it. If let's suppose this is the rock, on top of this rock you have the glacier which is moving, it will scoop out the rock as it moves due to the frictional force. And eventually it will carry out the smaller particles, very small particles from these rocks, and they will deposit them. So the glacial deposit made by glaciers, they are referred to as tillite or glacial till. So when you hear about the term tillite, or glacial till, these are basically very fine deposits made by glaciers. So wherever you find this glacial till or tillite, that will be the evidence that some point of time in the past, glaciers would have existed in that area. Glaciers would have moved in that area. And also, as the glaciers move, they create striations on the ground. Linear markings are created on the ground. Observe this. Observe this kind of a feature on the rock, where it appears as if the rock has been cut linearly. Observe these channels in these images. Right. Now, let me remove all these lines and notice this carefully. Now, this kind of linear pattern in the rocks can never be created by a river action, can never be created by wind action. This kind of a linear scooped out formation in the rocks can only be created where the glaciers have moved. And deposits can also only be created in regions where glaciers have moved. Now, upon studying the work of geologists, Wagner found out that certain very unique areas, they possess the evidence of glacial movement. For example, he found out that in the southern part of India, you have evidence of glacial movement. In the region of southern part of Africa, evidences of glacial movement. In the region of southern part of South America, evidences of glacial movement. Southern part of Australia, evidences of glacial movement. But if you take a look at the present climate in all these areas, there is no ice, no glacier in these areas. For example, if you take a look at the peninsular part of India or the southern part of India, you can never imagine the presence of ice in that area, let alone the movement of glacier. So what does that mean? can there be a case that climate has changed so drastically that at one point of time in history, glaciers would have moved in that area and now these regions are dry? Or the other possibility is that all these areas would have been together. And together where? In the region close to South Pole. And then they would have been separated. So the glacial evidences were found in regions in part of southern South America, southern Africa, in India significantly, peninsular part of India, even Aravallis for that matter, southern Australia. Now, if you bring all of them together, it gives you a clear-cut representation that all these places would have been together and they would have virtually experienced ice formation and glacial formation. These regions separated, moved away, and that is why you find the evidence of glaciers here 250 to 230 million years later. So this was another evidence. But on top of that, there was also evidence of fossils, fossils of ancient species, fossils which showed something remarkable. So based upon the paleontological evidences, these are also what come into the category of paleontological evidences. Evidences. Where it was found out that basically, for example, Mesosaurus is one of those species which created a lot of furor in those times. Mesosaurus is an ancient species out there which no longer exists. Now, Mesosaurus, based upon the study of their fossils, we do know that they were freshwater reptile. Freshwater means they could have existed in rivers, lakes, ponds, etc. Freshwater reptile with a length of around, hold on, at max 7 to 10 feet. That's it. A freshwater reptile having a length of 7 to 10 feet. Now, fossils of Mesosaurus were found in the region of South America, were also found in the region of Africa. Now, how is that possible? How is it possible that the same species, you find that if the continents were far away from each other, the same species is to be found thousands of kilometers away? This goes against the Darwin's theory of evolution, right? You cannot have the same species rising up in multiple places at the same time, isn't it? You cannot have the evolution process, evolution of species happening simultaneously at different times. For example, even humans, first of all, they appeared, it is said to that they have appeared in the region around Tanzania around 500,000 years back. Then they migrated into Asia through the land route. Then they migrated into the region of Europe and also into the region of America through the land route, where the eastern portion of Siberia appears to be connected, or at that point of time would be connected to North America. That is where the humans migrated, and then they populated North America, South America. Simultaneously, you cannot have evolution of humans in different portions, right? So how can you have simultaneous existence of fossils of Mesosaurus in the region of South America as well as in Africa? How can you have that? Now think about the absurdity of people who were trying to prove him wrong. People who were trying to prove him wrong. They knew that Mesosaurus is a freshwater reptile. It can never even swim through the oceanic waters. You know what is the contradiction that they provided? They said that you are saying Mesosaurus, if the fossil is present in South America as well as South Africa, now that can be because, and listen to this, the preposterous argument. They said that it can be possible that long time back in history, you might have had a land connecting these two areas, where the Mesosaurus would basically have traveled through for thousands of kilometers from South America to Africa. And that is why you find fossils in those areas. How absurd that is. Obviously, that cannot be possible. Obviously, the only explanation is that the land masses would have been together. But nonetheless, Nobody was ready to hear him at that point of time, because everybody was having the same mindset that the planet is contracting, and that is why you find the continents, etc., in the shape that they are. They were not ready to accept his point of view. But other than Mesosaurus, he provided other evidences also of Glossopteris, then Lystrosaurus, Sinognathus, all the various evidences he provided. But again, fell on deaf ears. Right? Now, he provided the nature in terms of the behavior of certain animals, such as lemmings also, where certain lemmings that you find in the region of Scandinavia, that is in the region of Norway, now they have a practice of where, under the conditions of harsh weather condition, when it starts becoming very, very cold, they straight away run to the west. Many of them fall into the ocean. But that tendency, that in case of hardship they start running to the west, that has been thought to be an evolutionary mechanism, where historically North American landmass would be connected with Europe, say, so they could have run to the region of North America. So all these behaviors of animal and the patterns in animal behavior, they were used to indicate the evidences that all the landmasses would be together and they would have separated. In fact, Wagner, the Pangea that he imagined was like this, right? Where you can see all the various different continents arranged, all the continents attached with each other, and they were separated from each other. Eventually, they were separated. Okay, initially you had these and this north-south separation, then from there also separation happened. Now, Wagner was convinced that there were two kinds of movements. One movement was the westward movement of the continents. Why westward movement of the continents? Types of movement. One, westward drift of continents. He was convinced that because North America and Europe, South America and Africa, they have similar rock systems, so they would have been joined together and they would have drifted to the west. North and South America would have drifted to the west, and they're still continuing to drift towards the west. So from that, he came across that the continents have a general drift to the west. Other movement that he was sure which happened was basically that all the various different continents here, all the continents were very close to the region of the poles, and then they have shifted to their present location. So this is a movement away from the region of the poles. So that is what he cited as movement away from poles. What was regarded as flight away from poles, or in German, what was actually his entire essay, his entire postulation was initially published in German. So that is where it was termed as pole flucht. Okay, so that was the movement away from the pole. So these were the two movements that he was sure was happening. Now comes the bad part. The bad part in the sense that till now, everything that he has said appears to make sense. All the evidences that he has provided appears to make sense. Now comes the portion for which he was ridiculed, he was made fun of. The reasons that he provided in order to support his theory. When you provide a theory, let's suppose you provide a theory that India behaves in a certain way, you have to provide the reasons to support your argument as well. That why are you saying so? Why are you coming at this particular conclusion? So just like that, in the case of Alfred Wagner also, he basically needed that, or he had to provide the reason why that drift is happening. So that is when he basically had certain assumptions also. So Wagner proposed, first of all, I hope we are aware about the intricacies of continental drift by now, that you had an initial supercontinent named Pangaea that broke into two parts, Laurasia and Gondwana land, that further disintegrated due to the westward drift and the polar fleeing force. And that is why you have the present day shape and the position of the continents in ocean. Now, on top of that, he proposed that, or assumption made by Wagner was the fact that continental masses move or float freely over oceans. Think about the absurdity of it. Obviously, Wagner was an individual who did not specialize in geomorphology or the geological aspect of geography. He specialized in the aspect of climate change and climatology. So he did not have much clue. And at that point of time, the science had also not developed so much to talk about the evidences of the interior of the planet Earth. So he had a set of limited information. So based on that limited set of information, he said that continental masses move or float freely over the oceans. This in itself is absolutely incorrect as it can be. But nonetheless, because he said that continental masses, please address my question. Is it true that continents or countries are still shifting, and after some years, India will be a little bit towards north? Yes, it is true. Is that the query? Is that satisfied now? What are ammonites? Is it fossil? Yes, it is fossil, as has been replied by the SME also. Is that satisfied now? Can we move ahead with that? Please understand, by the time that we are done with the continental drift theory and the plate tectonic theory, by the time that we reach the plate tectonic theory, we will talk about the formation of Himalayas. We will talk about what is going to happen 100 million years down the line. If you allow me the scope, again, I will reiterate, I will tell you why the Mediterranean Sea, where you see the Mediterranean Sea right now, there you will have the presence of mountains. Trust me, I will provide you much greater information than what you receive in the WhatsApp University and the social media accounts here and there, the YouTube shorts which are created. So don't worry about that. Have patience. Just follow what is being taught here. Okay, because if I find the same individual who is basically stressing upon that, if you are unable to understand the assumptions made, then please don't come complaining. Please pay attention here. I'll tell you what will happen to India going ahead into the future, whether there will be a fourth range of Himalaya getting created, whether the Mediterranean will get distorted or not, whether Africa will break into two or not, whether all the continents again will come together or not. We will talk about it. Okay, there is much greater amount of information which you are still not exposed to. Be patient, be receptive. Now, here, when we talk about it, the continental masses, they move or float freely over the oceans. Now, when you have the continental masses, basically think about it. Anything which floats over. Floating objects, they experience a force of buoyancy, right? I hope we are aware of about the force of buoyancy. That is an upward force. So force of buoyancy, right? You would also have experienced, let's suppose you have a bucket of water, you have a piece of thermocol, try to immerse that thermocol, try to sink it down. After some time, you will automatically find that the thermocol comes up and starts floating again, right? Why does it happen? What is that force which pushes the thermocol back up? In general, whenever you try to sink or drown anything which is light, it always comes up. That is the force of buoyancy. Any floating object experiences an upward force, that is the force of buoyancy. So Wagner said that because the continental masses are able to move or float freely over the oceans, they experience force of buoyancy. Force of buoyancy. This assumption was incorrect. Incorrect assumption. This was not correct. This he simply assumed because he did not have enough information about the interior of the earth at that point of time. But nonetheless, he had to prove these two types of movement. So, in order to prove these two types of movement, he cited reasons. For example, in order to prove the westward drift of continents, in order to prove the westward drift of continents, he cited the reason was gravitational pull by sun and moon. As the planet rotates from west to east, the force of gravitation would hold continents in their place and planet would rotate. What is the meaning of this? The reason that he cited. This is also what he cited as the tidal force, right? So basically, he said that look, you have planet Earth here, you have the presence of moon here, and then you have the presence of sun as well. Okay. Now here you have various different land masses. Okay. Now he said that the planet is consistently rotating in a direction of west to east, right? But simultaneously, you have a very strong gravitational pull subtended by the moon and a very strong gravitational pull subtended or extended by the sun as well. So, while that gravitational pull, as per Wagner, was nowhere as strong to attract the entirety of planet, but was definitely strong enough to hold the continents in their place. Because as per Wagner, continents are floating over the ocean, right? Imagine like a boat floating on the ocean. So that was his assumption. So he said that as the planet is, let's suppose this is the continent, the planet is rotating along with the continents. But because of the gravitational pull, the continent is held in its own place and the planet continues to rotate. So, if you are an individual, obviously at that point of time, humans did not come into existence. If you are an individual here and you were experiencing the planets to be held in their own place as the or the continents to be held in their place as the planet would rotate, basically you would arrive at the fact that the land would break, isn't it, as the continents would be held in their place and the rest of the continent maybe would have moved in a different direction, this continent would have been held in its own position, original position. So for an individual standing here, you would have experienced westward drift of continents, westward movement of continents. I will explain again. Suppose you have a large landmass. Suppose you have a large landmass. Wagner said that this landmass is floating over the oceans. And he also said that the gravitational pull extended by the sun and the moon are so very strong. They cannot hold the earth in its place, but as the earth is rotating, they can definitely hold the continents in the place. So the continents, they will be bound to be present in this position as the rest of the planet rotated. That meant that there would be cracks and the breakage, and rest of it would move like this. Maybe some portion of the continent would be held in its place, indicating a westward drift. So he basically used the force of gravitation as the justification for the westward drift. Obviously, this was incorrect because the gravitational pull, had it been so strong by the sun and the moon, had the gravitational pull been so strong, the entire rotation of planet would have come to a complete standstill within 50,000 years. Planet Earth would not have been rotating till now if the gravitational pull extended was so high. So this was an incorrect reason. The other reason that he was providing was to support the movement away from the poles. Movement away from poles. He said that basically all the different continents, they are moving away from the region of the poles into the region around equator. That is, they are moving, all the various different continents, etc., they are moving towards equator. Here also, they are moving towards equator. Now, why is this? So this, he said, is a combination of centrifugal force due to combination of centrifugal force and force of buoyancy. Now the planet is continuously rotating around its axis in a direction from west to east, right? Any object which moves in a, what is centrifugal force? So any object which moves in a circular motion experiences a force away from center, isn't it? So any object which moves in a circular motion experiences, any object, let's suppose, it experiences a force away from center. That is your centrifugal force. Across the entirety of planet Earth, the centrifugal force will be maximum where? Where the speed of rotation is the maximum. Where is the speed of rotation maximum? Around the region of equator. So the centrifugal force will be maximum around the region of equator. Right. So centrifugal force is maximum around equator. So he said that the force of buoyancy, which is already keeping the continents afloat, combined with the centrifugal force, is pushing all the very different continents towards the region of equator, away from the region of poles. That is what he cited as the reason for the pole flux. Obviously, this is also incorrect. Why? Because there is no such force of buoyancy which is acting upon it. There is no such force of buoyancy which is floating over, or the particular continental landmass is not floating over the oceanic area. So no such force of buoyancy exists. So because of these reasons, his theory was basically discarded, because both the reasons and the assumption that he made, both of them were incorrect. And that is why Wagner's theory was basically eventually rejected. Having said that, it did provide evidences, it did provide the concept that the continents indeed can move, and hence, in many of the respects, in many of the circumstances, Wagner is referred to as the real pioneer who helped devise the theory of plate tectonics. And eventually, our understanding of how the planets, land, etc., behaves, that understanding was provided by Alfred Wagner. Okay? Yes, that is where we'll end the session. And all of you, you can leave. Okay? All those who don't have doubts, you can leave. Okay? Avnish, we'll discuss it on Monday. We don't have time now. So that will be all from my side. No, Seema, we can't discuss PYQs. Many of you have a strict foundation of time. So obviously, we'll be discussing it on Monday. In which theory Tethys is mentioned? Tethys is about the aspect of origin of the Himalayas, Surya. That when the Himalayas got created, in that process, we will talk about it on Monday, if time permits, that how this Tethys Ocean, etc., that was subsumed as the land basically moved north and eventually led to the creation of Himalayas. Holidays for Diwali. Sunday is a holiday. Uh, will we discuss how the Rajasthan became desert? Sunny, I will, if you allow me, I will discuss even the fact about how each and every portion of India came into existence, how the origin of India happened. But again, I will always maintain that the level of discussion that you will observe in the class is very much a sum product of the candidates that are present. If you are supportive enough, I am ready to take the level of discussion as much as possible, as high as possible, talking about the aspects of future, what happens in the future, etc. But in case the class response is such where even the generalistic portions are more than adequate for many of you, as it appears to be, we will keep it up till that only what is adequate for GS. So as we move ahead, depending upon the demands and the understanding ability of the class, we will move ahead. So the continental drift theory was rejected. Yes, my dear friend. Coriolis force and centrifugal force. Oh my God. Centrifugal force is basically whenever you have any object which is rotating in a circular motion, it experiences a force on the outside that is referred to as centrifugal force. Coriolis force is exerted on any free moving object due to the rotation of the planet. As the planet rotates on its axis, different areas rotate at different speed, due to which any object moving in the northern hemisphere bends to their right, any object moving in the southern hemisphere bends to their left. Okay. How the species created on earth? So it happened due to evolution, the entire process of evolution. So the origin of species, Harshita, is said to have happened around 3 to 3.5 billion years back, when you had the microorganisms in the form of cyanobacterium, which were basically chemotrophs. They synthesized the chemicals around them to produce oxygen and food. So those chemotrophs, they came into existence. That is when multicellular organisms, they came eventually. And the various different varied species that we had, they came into existence around 600, 500, 600 million years back. Humans came into existence very recently, few 100,000 years back. We are amongst the latest additions. Okay. Ziba, according to Wagner, when did the bifurcation of landmass started? So he basically was not very clear about when all the landmass started separating, but he was clear that the Gondwana land and the Angara land, even amongst the Gondwana land, the separation was initiated roughly around 200 million years back. Okay. Now we know that the entire Pangea, now with the help of radiocarbon dating, etc., we do know that the entire Pangea formation was something which was prevalent around 300 billion years back. And eventually that separated. Now we also know that even before Pangea, only if you are interested in this, before Pangea, you had multiple such supercontinents. So the planet goes through these cycles quite often, where the supercontinents they get created. They then break into smaller parts. All the smaller parts they drift, they move away, again they get together. Again you have a supercontinent, again they break, and again they have smaller parts. Again they will come together to form a supercontinent. So Pangea is actually the third supercontinent that the planet has witnessed that we know of ever since its evolution, right? And it is postulated that in the next 225 million years, again, all the land masses across the planet, they will get together to form another supercontinent, the next Pangea, so to say. Whether the size of Theia is equal to the Mars or thrice to its size. No, Mars-like object. It is always referred to as, Theia is referred to as a Mars-sized object. Komal. Payal, sir, as said by Wagner, Sial represented continental landmass which could float freely over seema or oceanic crust. This theory is same as said by Edward Seuss. Is it true? No. So, what Alfred Wagner borrowed about the movement of continents and the internal structure of it, Payal, was straight away from the internal structure provided by Edward Seuss. Edward Seuss, understand why that happened. Edward Seuss was a very famed Austrian geologist who specialized in the interior structure of planet Earth in the 1800s. Now, think about it. German meteorologists will obviously borrow the ideas easily available from a very famous Austrian geologist very close nearby, right? Having the same particular territorial domain. So that is why he borrowed it. And Edward Seuss, he provided many theories to a great accuracy. For example, the theory for the formation of northern plains in India, explained particularly well by Edward Seuss, right? So he had his moments of glory, and that is why Wagner borrowed his concept. The reason for gravity of moon is also the presence of Nephi or anything else. Sham, any object which has mass will have a gravitational pull of attraction. Moon has a mass which is around one-sixth of planet, which is much less than planet Earth. Hence, the gravitational pull is also. Nephi is not responsible for gravitation. Earth has got its large amount of mass that is responsible for gravitation. Okay. Remember, Newton had said that I can attract a star with my finger because my finger also has mass and the star also has mass. It is just a matter that because my finger is so very small, the gravitational pull will be very small, but it will be there. It will not be zero. Okay. So, Dhyan, hence the Wagner's force of buoyancy was the initial forced concept that made all the three reasons fail. Yes. Perfect. Avnish, in upcoming sessions, are we also going to discuss about types of forest like tropical, temperate, deciduous? Yes. In Indian geography, we'll discuss. Other than that, in the portion of environment ecology, also, if I get a chance to conduct the class, I'll discuss there also. What's the reason cited by Wagner for pole flux? Kambapati, the combination of the centrifugal force along with the force of buoyancy. Okay. Yes, both the assumptions were incorrect. Right. Ananya, the theory of continental drift was rejected because of incorrect reasons and the assumptions made by Alfred Wagner. Okay. Right. About note making PYQs, obviously today we don't have time, so we'll discuss it on Monday. Even continental drift theory was discarded, the non-permanency of landforms retained. Can we quote this as conclusion? You can, but generally the question which is asked is mostly about the very direct about the evidences of continental drift theory and how it led to the formulation of plate tectonic. Those kind of questions are asked. Okay. And why the last reason is incorrect? Because you don't have such force of buoyancy acting on the continents which will push them towards the equator. Vijay, my dear friend, I'm trying to find your question. I'm unable to find your question here. Himalaya mountains were formed under the same conditions. Why the northwest side was not formed? Himalaya mountains were formed under the same conditions. Why the northwest side was not? We'll come talk about the formation of Himalayas. You will understand in detail. if this question is asked in the exam, the conclusion would be that, depending upon what the question is, if the question is that, let's suppose, what do you understand by the theory of continental drift, discuss the prominent evidences. So eventually you have to talk about the fact in the conclusion that even though the reasons and assumptions made by Wagner were discarded, they were incorrect, but nonetheless this proved to be substantially important in the postulation of future theories that plate tectonics, etc. Okay, so that is where we'll end the session here today. We have exceeded the time. We'll end the session here today. We meet again on Monday. Till that point of time, do take care of yourself. Enjoy have a safe and festive Diwali. Until we meet again, goodbye. Thank you.